At some point, if you look far enough into space, you stop seeing stars. You start seeing time. Every photon from a distant galaxy carries a message from the past. It is a perfect, pristine snapshot of what the universe looked like billions of years ago. But there is a boundary, a final wall that we cannot cross. This is true no matter how powerful our telescopes might ever become. This is not because of a limitation in our technology. It is because of a fundamental limit imposed by physics itself. Beyond that, cosmic edge light has not had enough time to reach us. This is since the beginning of the universe. It's a cosmic horizon, and it limits not just what we can see, it limits what we can ever possibly know about the universe we inhabit. But what if we could somehow reach further? What if we could build telescopes so advanced they could peer beyond that final boundary? What if we could discover methods so profoundly strange? What has NASA already seen lurking near that cosmic edge? This is a journey through the absolute limits of our observation. It is a journey into the terrifying, beautiful mystery of what might lie just beyond. When telescopes first opened up the heavens, nobody had ever truly seen space. This was in the early 1600s. People had looked at the night sky with their eyes alone for all of human history, and for thousands of years that was more than enough. The stars were tiny, unchanging lights. The moon was a mysterious, glowing disk that waxed and waned. The planets, the wanderers, moved in strange ways against the fixed backdrop of the stars, but their details, their true nature, remained completely invisible. Then came a simple, almost crude device. It was two pieces of carefully ground glass in a tube that changed everything. The telescope didn't start out as a noble tool for astronomy. The first known working versions were built in the Netherlands around 1608. They were built by spectacle makers. They were used mostly by merchants and soldiers. The device, a spyglass made faraway ships, looked closer. This was an invaluable advantage in trade and in war. It was a clever trick of lenses useful for spotting danger or tracking goods at sea. But when news of this remarkable invention spread across Europe, it caught someone's attention. It caught the attention of someone who saw a completely different use for it. Galileo Galilei. Galileo didn't invent the telescope, but he made it infinitely better. He taught himself the art of lens grinding. With a craftsman's patience, he built more powerful versions than any before. Then, in the autumn of 1609, he did something no one had thought to do. He turned his improved spyglass toward the night sky. That single, simple moment marked the beginning of a new age. This was not just for astronomy, but for how we as a species think about the universe. It changed how we think about our place within it. The heavens had seemed still perfect and divine for all of human history. They were about to become full of movement, detail, and unsettling imperfection. The universe, which had seemed calm, ordered, and centered on us, was about to surprise everyone. One of Galileo's first targets was the moon. For centuries, people had thought it was a perfect, smooth, polished sphere. This was following the teachings of Aristotle. They thought of it like a celestial crystal. But through the telescope, Galileo saw something very, very different. He saw mountains casting long, sharp shadows. He saw deep valleys and vast circular craters. The shadows moved across the lunar ridges as the sunlight hit them. This happened at different angles, just as shadows move across mountains on Earth. The moon was not a perfect, ethereal object. It was rugged, broken, and imperfect, just like our own world. Next, he looked at the planet Jupiter. What he found there was even more shocking. It was far more dangerous to the established order. Orbiting around the giant planet were 4 tiny, distinct points of light. Night after night, he watched them, and they moved. Sometimes they would disappear behind the planet, then reappear on the other side. These were not fixed stars. They were moons, tiny worlds revolving around something other than the Earth. This was the first time that anyone had seen clear, irrefutable evidence. Not everything in the universe revolves around us. The Earth, it seemed, was not the center of everything after all. Galileo's discovery was a direct observational challenge. It challenged centuries of religious and philosophical belief. He also turned his telescope to the Milky Way. To the naked eye, it looks like a pale, ethereal smear of light. It looks like a celestial river across the night sky. But through the telescope, it exploded into thousands upon thousands of individual stars. What had seemed like a single hazy band was actually made of countless lights. The universe was not sparse and empty. It was packed with stars stretching far beyond what anyone had ever imagined. Each of these discoveries chipped away at the old comforting ideas. The mountains on the moon, the moons of Jupiter, the stars of the Milky Way. For centuries, people had believed that the heavens were fixed, perfect, and unchanging. The planets were supposed to move in perfect divine circles. The stars were thought to be placed on a vast crystal sphere that enclosed the Earth. Everything beyond our world was part of a divine, unchanging, and perfect order. But now the telescope was showing craters and motion and moons. It was showing countless mysteries. The sky was not calm. It was full of action. These early telescopes were incredibly primitive by today's standards. They had narrow fields of view. Their images were often blurry, and they suffered from chromatic aberration. This created rainbow-like distortions around bright objects. Still, they gave people a glimpse of a reality they had never known, a universe that was far larger, more complex, and less centered on humanity. It was a universe less centered on humanity than anyone had dared to dream. And just as important as what the telescope revealed was what it made possible. It established a new pattern in human history. Better tools let us see more, and the more we see, the more profound questions we have. This pattern tool discovery deeper mystery has repeated itself again and again. It has repeated from Galileo's spyglass to the James Webb Space Telescope. The first telescope showed that the moon had terrain and that planets had moons, so better telescopes were built. With those astronomers found more moons, the rings of Saturn, faint stars and comets. They found strange fuzzy objects that didn't follow any known pattern. They found the planet Neptune by watching the orbit of Uranus wobble. This gravitational perturbation hinted at an unseen world. They discovered galaxies beyond our own by seeing faint spiral smudges of light. With more powerful instruments, these smudges turned out to be island universes. Each contained billions of stars. The telescope opened up the sky, but it also showed us how much more there was to find. Galileo wasn't alone for long. Others quickly joined the effort. Johannes Kepler improved the design of refracting telescopes. He had already worked out the laws of planetary motion. He used them to better understand the architecture of the solar system. Later in the 1660s, Isaac Newton created a new type of telescope. It used mirrors instead of lenses to gather and focus light. This allowed for much clearer, sharper images. It avoided the rainbow-like distortions of early lens-based telescopes. Each technological step forward revealed more of the universe. It revealed more of its strange and unexpected behavior. Why deep space is a time machine. When we look up at the night sky, it feels like we are seeing the stars as they are. We feel we see them right now in this very instant. But that's not quite true. What we're really seeing is what they looked like some time ago. That's because light, the cosmic messenger, doesn't move instantly. It travels at a fixed finite speed. A very fast speed, yes, but not an infinite one. The light from our moon takes about 1.3 seconds to reach the Earth. Our moon is our closest celestial neighbor. The light from the sun takes a little over 8 minutes. So when you look at the sun, you are seeing it as it was 8 minutes in the past, though hopefully not directly. If the sun were to suddenly vanish, we would have no idea for a full 8 minutes. We would continue to orbit a ghost. The deeper you look into space, the older the light becomes. This simple fact has enormous mind-bending consequences. It affects our understanding of the cosmos. When we look at a star that is 100 light-years away, we see its past. We are seeing it as it was 100 years ago. When we look at a galaxy that is 1 million light-years away, we see its past. We are seeing it as it was 1 million years ago. The farther away something is, the further back in time we are looking. In this way, space itself becomes a kind of time machine. In our everyday lives, this time delay is so incredibly small that we don't notice it. Even the radio signals we send to the Moon or Mars rovers are slightly delayed, but they are still close enough that we can interact with them in nearly real time. But space is huge. Once you get beyond our own solar system, the distances stretch so far. Even light traveling at a staggering speed takes years to get here. It travels at nearly 300,000 kilometers per second. It takes years, thousands of years, even billions of years to get here. Telescopes are designed to collect the faint light from objects that are far away. This is especially true for the massive ones on remote mountaintops or in space. Some of that light has been traveling through space for billions of years. It has traveled since before the Earth was even formed. One of the clearest examples of this came with the Hubble Space Telescope. In the mid-1990s, a team of scientists made a bold decision. They pointed the Hubble at a tiny, dark, seemingly empty patch of sky. This was in the constellation Ursa Major. This spot was no bigger than a grain of sand held at arm's length. And from Earth, even with powerful ground-based telescopes, it looked empty. There were no bright stars, no obvious galaxies, just an inky blackness. They kept the telescope focused on that one tiny spot for over 100 hours. This was spread out over 10 consecutive days. This allowed the faint, ancient light to slowly accumulate on its digital detectors. As the long exposure built up, the image began to change. First, a few faint smudges appeared, then hundreds. By the end, there were thousands of tiny, colorful shapes. These were not stars, they were galaxies, each one filled with billions of stars. Some of them were so faint and so red that they were barely visible. They were pushing the limits of what even the Hubble could detect. Those reddish colors were vital clues. Because our universe is expanding, the light from distant galaxies is stretched. It is stretched as it travels across the growing fabric of space. This stretching of the light waves makes the light appear redder. It appears redder than when it first left the galaxy. It's a phenomenon that astronomers call redshift. By measuring this redshift, astronomers could tell how far away the galaxies were. Therefore, they could tell how far back in time we were seeing them. Some of the faintest, reddest galaxies were from a time when the universe was young. This was a time when the universe was less than 1 billion years old. They had been sending their light toward us for over 12 billion years. We were seeing young baby galaxies from the early days of the universe. This was a profound turning point in our understanding of the cosmos. The Hubble Deep Field, as the iconic image came to be known, proved something. It proved that even the quietest, most seemingly empty part of the sky was packed. It was packed with the ancient light of thousands of galaxies. And the better our tools get, the further back in time we can go. With new instruments, scientists began to look even deeper. This was especially true with ones sensitive enough to detect infrared light. Infrared is crucially important because the oldest, most distant light has been stretched. It has been stretched so much by the relentless expansion of space. It no longer appears as visible light at all. Instead, it shows up in the infrared range of the electromagnetic spectrum. This is a range that our eyes cannot see, but our telescopes can detect. The James Webb Space Telescope was designed with this exact purpose in mind. It was launched years after the Hubble. Its massive gold-coated mirror and ultra-sensitive infrared detectors were built specifically. They were built to catch the faintest, oldest light in the universe. And it is already finding galaxies from just a few 100 million years after the Big Bang. That might sound like a long time, but in the history of the cosmos, it is close. In the 13.8 billion year history of the cosmos, it is incredibly close. We are now able to see these galaxies as they were when they were first forming stars. They were gathering gas and merging with other young galaxies. We are watching their early lives unfold. This is long before they became the large, mature galaxies we see today. The deeper we look, the younger the universe appears. Eventually, if we look far enough back in time, we reach a kind of wall. This is a final, impenetrable barrier. This is the point in cosmic history when the universe was too hot and dense. This was about 380,000 years after the Big Bang. Light couldn't travel freely. The entire cosmos was an opaque, glowing fog of plasma. This moment when the universe cooled enough for atoms to form has its light. The light from this moment still exists. It was when space became transparent. It fills the entire sky, though we cannot see it with our eyes. It is called the cosmic microwave background, or CMB. It is the oldest light that we can possibly observe. This background light is like a baby picture of the universe itself. It shows us a time when everything was packed tightly together. Tiny, almost imperceptible changes in the temperature of this light were seeds. These variations were of just a few millionths of a degree. Over billions of years, these seeds grew into vast cosmic structures. They grew into galaxies, stars, and planets. We've mapped this background radiation in exquisite detail. We used a series of dedicated satellites like COBE, WMAP, and Planck. Each new map brings us closer to understanding how the universe began. It helps us understand how it grew into the complex, structured cosmos we see today. New telescopes on Earth are preparing to search for the very first stars. They are using giant mirrors and complex computer systems to sharpen their images. They search for the population 3 stars, the very first sources of light in the cosmos. These stars were likely massive, incredibly bright, and very short-lived. They helped to shape the early universe, but they have remained hidden. They are so far away and so faint that they are beyond our current instruments. It may take years or even decades, but someday we may finally catch a glimpse. And when we do, we will be seeing a moment that happened over 13 billion years ago. The great limit. Why the universe doesn't let us see forever. The universe is about 13.8 billion years old. That is how long that light has had to travel since the beginning of time. So when we look out into space, the most distant thing we can see is this light. This is the light that has been traveling toward us for that entire duration. Anything that is farther away than that simply has not had enough time. It has not had enough time to send its light to Earth. That light is still on its way, or it hasn't even begun its long journey yet. So we cannot see it, and we may never be able to. This boundary is called the observable universe. It is like a bubble that is centered around us. From our position in space, the light from all directions forms a sphere of visibility. We are at the very center of our observable universe. This is not because we are special, but simply because that is how observing works. Every place in the entire universe has its own bubble. It has its own observable universe. If you were standing on a planet in another galaxy, your view would be different. Your observable universe would be centered on you, but your view would reach a different set of galaxies, a different set of stars. The universe in all likelihood goes on far beyond this limit. It may go on forever, but we are locked inside the part that we can observe. If the universe is 13.8 billion years old, the distance should be clear. Shouldn't the farthest thing we can see be 13.8 billion light years away? That would seem to make logical sense, but it's not quite right. The universe has been expanding the entire time that the light has been traveling. That means that the distance to the farthest galaxies we can see is much larger. It's more like 46 billion light-years. The light left those ancient galaxies when they were much closer to us, but the fabric of space itself has stretched since then. It has pulled those galaxies much farther away. So even though we are seeing ancient light, the source is now at a more distant location. This expansion is part of what makes the universe so hard to wrap our heads around. Space itself is growing. It is not that the galaxies are flying through space like rockets. It is that the very fabric of space between the galaxies is stretching. This stretching carries the galaxies away from each other. This happens even if they are not moving on their own, and it affects the light that is traveling across that space too. The longer the light moves, the more it gets stretched out. If we want to look even further back, we will need something other than light. We need to look to the very first moments after the Big Bang. Some scientists are searching for gravitational waves. These are ripples in the fabric of space-time itself. They might have come from the earliest fractions of a second after the universe began. These primordial waves, if ever detected, could give us a new way to see. We could see through the cosmic fog, but right now they remain hidden just beyond our grasp. This built-in limit isn't just a challenge for our telescopes, it is a fundamental part of our reality. We can never observe beyond this cosmic horizon. This is because of the very nature of time, light, and space. It is like trying to hear a sound that was made before your ears existed. It is possible that the universe goes on far beyond what we can observe. In fact, most scientists believe it does. The part that we can see is only a tiny finite slice of a much larger whole. This larger whole may possibly be infinite. There may be regions of space with different galaxies and different clusters. They may even have different physical conditions, but they are forever out of our reach. The expansion of the universe is happening so fast that some regions are moving away. They are now moving away from us faster than the speed of light. That might sound like a contradiction of Einstein's theory, but it isn't. According to general relativity, space itself can expand faster than light. This does not break the rules. This is because it is space that is expanding, not objects moving through space. And when that happens, the light from those regions can never reach us. Not now, not ever. This means that some of the galaxies that we can see today may one day disappear. Their light will continue to stretch and to fade until it can no longer be detected. In fact, many of the galaxies that we see in our deepest images are already beyond our reach. The ancient light that we are seeing from them now left those galaxies billions of years ago, and since that time the space between us has stretched so much. No new light from them will ever be able to reach us. These galaxies are like cosmic ghosts already lost to the growing, accelerating dark. How photography freed the night sky from the human eye. For centuries, the telescope had one main user, the human eye. Even as the telescopes grew bigger and more powerful, they still relied on a person looking through an eyepiece trying to sketch what they saw. They tried to sketch it before it faded from memory. The sky revealed more than it ever had before, but it was still plagued by the fundamental limits of our own human vision. Our eyes are quick, but they are also incredibly weak. They can only take in so much light, and they tire very easily. Faint stars, distant nebulae, and soft ethereal galaxies all remained hidden. They were too dim to leave a lasting impression on the human eye. In the 1800s, photography arrived. At first, it was a slow, clumsy, and very difficult technology to use. Early cameras needed extremely long exposure times. They produced fragile, one-of-a-kind images on glass or metal plates. But they had one major revolutionary strength that the human eye did not. They could collect light over time. While your eye sees a single moment and then moves on, a photographic plate does more. It keeps absorbing the light, keeps accumulating the photons the longer it is exposed. This meant that a camera could stare at the night sky for minutes or even for hours. It could build up the faint light from stars and objects that no human eye could ever see. The night sky was no longer limited to what a person could sketch from a fleeting memory. It could now be recorded, studied, and revealed in its full, deep glory. The first real success came in 1840. John William Draper, a scientist in New York, used a telescope to take a daguerreotype. This was a picture of the moon. It wasn't sharp or detailed by today's standards, but it proved the core idea. You could aim a camera through a telescope and let the sky leave its own permanent trace. Over the next few decades, others followed. Some of the earliest astronomical photographs showed star clusters and planets. One of the big breakthroughs came in 1880. Henry Draper, the son of John Draper, took a long exposure photograph. He took a photo of the Orion Nebula. It showed a cloudy, ethereal swirl of gas and stars. It was far beyond what any human eye could pick up through a telescope. The image was definitive proof that photography wasn't just a tool for copying. It was not just for copying what people could already see. It was a tool for revealing things that no one had ever seen before. With these long exposures, astronomers discovered that space was full of faint, hidden objects. These included nebulae galaxies and star-forming regions that could not be seen before. A telescope used with the human eye might reveal a few dozen stars in a patch of sky. That same telescope, when paired with a photographic plate, would reveal hundreds. With a night of patient observation, it could reveal even thousands. The longer the exposure, the more of the hidden faint light poured in. The universe began to grow deeper, layer by layer. Another key figure was Edward Charles Pickering at the Harvard College Observatory. In the late 1800s, he and his team of computers used photography. Many of them were women, including the brilliant Annie Jumpcannon. Henrietta Swan Leavitt was also part of the team. They used photography not just to capture simple images, they used it to study the light from the stars themselves. By photographing the spectra of stars, they could classify them. Spectra are the rainbows created when starlight is split by prisms or gratings. They could classify the stars by their type, temperature, and brightness. This meticulous work laid the foundation for modern astrophysics. One of the most important uses of photography came in 1887. An international project was launched to create a full photographic map of the sky. It was called the Carte du Ciel, or Map of the Sky. This massive, ambitious effort involved 18 observatories from around the world. Over the next few decades, they took more than 20,000 photographic plates. Each one captured a different small region of the heavens. It was the most ambitious data collection project of its time. In 1890, the Harvard Observatory published the first volumes of a catalogue. It was the Henry Draper Catalogue, which classified hundreds of thousands of stars. These classifications, all based on the analysis of the photographic plates, helped uncover something. They helped to uncover a deeper structure in the cosmos. They revealed that stars were not just simple points of light. They were complex physical systems with their own life cycles and properties. The true power of photography became even clearer when astronomers noticed changes. Since the photos could be stored and compared over time, it was now possible to spot variables. These were stars that changed in brightness over time. It was even possible to spot entirely new events like novae or supernovae. If a star had exploded in a far-off galaxy, it might have been too quick to be seen. It might have been too faint for the human eye. But it would leave its permanent mark on a photographic plate. That plate could be pulled from a drawer days or weeks later and studied at length. By the early 20th century, photography was the main engine of astronomical discovery. The telescopes were now being designed specifically to work with the cameras. Large photographic telescopes were built to scan wide areas of the sky. Each plate captured tens of thousands of stars. Some of the observatories had entire teams dedicated to examining these plates. They would mark the changes, measure the distances, and find the patterns. One of the most iconic examples of photography's power came in 1923. The astronomer Edwin Hubble used the 100-inch Hooker telescope. He used it to photograph a blurry object called the Andromeda Nebula. On one of his plates, he spotted a variable star, a Cepheid. Its changing brightness allowed him to calculate its distance. The result was staggering. The Andromeda was not a cloud inside our galaxy, as many believed. It was its own galaxy, millions of light years away. This one photograph broke the known universe wide open. What people thought was the whole of creation, the Milky Way, was now just one galaxy. It was one among countless galaxies. Space was vast beyond imagination. Long exposure photography also showed how messy and dynamic space really was. It showed the dust lanes cutting through galaxies like the stars. It showed nebulae glowing in delicate reds and blues. It showed star clusters spilling across the sky like spilled salt. The universe was alive, textured, and full of movement and light. Perhaps the most poetic part of this change was that photography did not just help astronomers. It also let ordinary people see what was out there. A photograph could be published, copied, and shared. It could be printed in books and shown in museums. People who never owned a telescope or who lived in bright cities could see the stars. They could now hold the sky in their hands. A single image could say more than 100 drawings. By freeing the sky from the eye, photography opened a new phase of exploration. But more than anything, it changed our relationship with the night, the darkness before a light. What came before the first stars, after the light of the Big Bang was released, the universe entered a strange and silent time. The CMB began its long journey through space. The universe had expanded and cooled enough for atoms to form, but the stars had not yet appeared. The bright fireworks of creation had faded. There were no new sources of light to take their place. For hundreds of millions of years, the universe existed in darkness. There were no stars and no galaxies. There was just cold hydrogen gas drifting through space. This was the time known as the Cosmic Dark Ages. It is a period that remains one of the most mysterious in the history of the universe. It is a long stretch of time between the last light we can detect from the early universe. It is between that light and the first light we can see from the stars and galaxies. To find out what happened during this hidden chapter, astronomers have worked hard. They have worked like detectives, piecing together tiny clues. They have run computer models and followed traces left in the cosmos today. During this time, the universe was filled with neutral hydrogen. These were atoms with a single proton and a single electron. After recombination, the moment when electrons and protons combined to form atoms, the photons that had once been trapped in the hot plasma were finally free. That is the light that we see as the CMB. But once that light moved on, there was no new light to replace it. No stars had formed yet. Space was not completely black, but it was cold and quiet. This darkness was a calm before the storm. Gravity was at work in the background, slowly pulling matter together. These clumps started out as slight differences in density. They were small ripples in the early universe. Some of the areas had just a little more matter than others. Over time, those areas pulled in more gas. As the universe expanded and cooled, these dense pockets grew. They were the seeds of the future stars and galaxies. But during the Dark Ages, they were still invisible. The challenge of observing this time comes down to how we see the universe. Light is the messenger that we use for almost everything. Whether it is visible light, radio waves, X-rays, or microwaves, we rely on photons. We rely on them to bring us information from space. But during the Dark Ages, there were no strong sources of light to send us messages. The hydrogen gas was cold and neutral, and it did not glow. There is, however, one signal from this time that astronomers have been trying to detect. It is the 21-centimeter line. This is a very faint radio wave that is produced by hydrogen atoms. Under very specific conditions, a small amount of energy is released. This happens when the spin of the electron in a hydrogen atom flips. It flips relative to the spin of the proton. This energy is released in the form of a radio wave. It is incredibly weak, but because hydrogen filled the entire universe during the Dark Ages, it should be everywhere. If we could detect this signal, it would give us a map of hydrogen across space. It would show us hydrogen before the first stars were formed. But detecting this signal is extremely difficult. Over the billions of years, the 21-centimeter radiation has been stretched. It has been stretched by the expansion of the universe. It is no longer at 21 centimeters. It has been stretched to longer wavelengths now in the meter range. That makes it even weaker and harder to find. On top of that, the Earth is filled with radio noise from human activity. Cell towers, satellites, radio stations, and even lightning can drown out the signal. To really study this Dark Age radio wave, we may need to go somewhere quiet. We may need to go to the far side of the Moon, which is shielded from Earth's interference. Some experiments like the JWST project in Australia are trying to detect this signal. In 2018, JWST announced a possible detection of the signal. The signal was from the time just before the first stars. The result was surprising and controversial. The signal seemed to be stronger than expected. This could mean that something odd was happening back then. Maybe dark matter was interacting with hydrogen in ways we do not yet understand. Or maybe there is something else entirely that we are missing. More data is needed, and other experiments are being built to double-check the result. Even though we cannot see the Dark Ages directly, we know that they must have happened. Without this quiet period, the stars would not have formed the way they did. The galaxies would not have grown. It was during this time that the large-scale structure of the universe began to take shape. The filaments of gas stretched across space, forming the cosmic web. The dense nodes grew into galaxies. The gaps became the vast voids that we see today. All of this happened in the dark. Eventually, the darkness ended. Somewhere in this deep silence, the first stars began to form. They were probably massive ones, burning hot and bright. They were made from pure hydrogen and helium. These stars lived fast and died young. But when they lit up, they changed everything. Their light began to break apart the hydrogen atoms in space. They turned the neutral gas into charged particles once again. This era, called reionization, marks the beginning of the light-filled universe. But until that moment, the universe was a shadowy place. It was full of matter, motion, and potential, but without any real light. It is hard to imagine such a time because every view we have of space today shows stars. It shows galaxies and glowing clouds, but all of that had to come from somewhere. The cosmic Dark Ages were the waiting room for everything. The stars that we now admire were being prepared during this time. They were hidden in darkness, shaped by gravity, and quietly getting ready to shine. The mystery of this era still pulls at astronomers. What were the first stars really like? How big were they? How many of them were formed at once? Did they come together slowly, or did they burst onto the scene in great numbers? These are the questions that we cannot answer yet. But as technology improves, we might begin to unlock this hidden age, as we learn to listen for signals in ways we have never tried before. The faraway galaxies that shouldn't exist. According to current theories, galaxies take time to grow. After the Dark Ages ended, the first stars lit up and began to collect into clusters. Those clusters merged and gathered gas, slowly building up. They built up into the large spiral and elliptical galaxies that we see today. This process was expected to take hundreds of millions of years, even billions. But some of the early galaxies that the JWST has found were already large and bright. They were large and bright when the universe was still in its infancy. These galaxies are strange in other ways too. Some of them appear to be very dense, packed with stars in small spaces. Others show signs of having well-formed structures. These should not have had time to develop. In one case, astronomers saw a galaxy that looked so bright, it would have had to form stars at a pace far beyond anything seen today. That is a red flag. If these galaxies are truly as old and massive as they seem, we are wrong. It means that either we are wrong about how galaxies form or something else is happening. At first, some scientists thought that there might be a mistake. Maybe the galaxies were not as far away as they seemed. The distances in space are often estimated by looking at redshift. But redshift can be tricky, especially in early data. Other things like dust clouds or certain star types can mimic the colors of distant galaxies. So follow-up studies began. In several cases, the results held up. The spectroscopic observations confirmed the extreme redshifts. These really were ancient galaxies, and their brightness and mass estimates remained high. The mystery deepened. Some researchers tried to adjust the models to see if early galaxies could grow faster. Perhaps star formation in the early universe was more efficient. Maybe there were more dense regions of gas. Or maybe black holes and violent feedback loops helped to accelerate the process. But each idea brings more questions. If galaxies were formed this quickly, then what does it say about the universe's timeline? If large structures existed this early, it could mean our understanding is missing something. Our understanding of cosmic evolution is missing key ingredients. The standard model of cosmology is called ΛCDM. This stands for lambda cold dark matter. It has done a good job of explaining much of what we see. It describes how dark matter helps to pull normal matter together. This forms the skeleton of the cosmic web. It also accounts for the expansion of space driven by dark energy, but it relies on the idea that things build up slowly. If galaxies grew faster than expected, it could mean something is different. It could mean dark matter worked differently in the past, or some other force was at play. Another possibility is that what we call the Big Bang timeline might need to be tweaked. Not the Big Bang itself, but the rate at which the early universe evolved. If the physics of the early universe were slightly different, things would change. If, for instance, expansion slowed down earlier than we thought, then the structures would have had more time to grow. But that change would affect everything from the formation of elements to the CMB. So far, the other pieces of the puzzle do not suggest a major mismatch. That makes the existence of these galaxies even harder to explain. Some scientists have even wondered if we are looking at something else entirely. They might be objects that only look like galaxies. They could be powered by black holes or bursts of energy. Maybe these are early quasars with bright disks of gas swirling around them. Maybe they are clusters of stars with strange properties. But these explanations feel like stretches. The observations are clear. We are seeing large, complex structures at a time when the universe was still young. This is not the first time that something like this has happened in astronomy. History is full of discoveries that did not make sense at first. When people first saw spiral galaxies, they did not know what they were. When Edwin Hubble proved that galaxies lay far outside the Milky Way, it changed things. It shattered the idea that our galaxy was the entire universe. Each time the sky surprised us, and each time it forced science to grow. That may be happening again. The JWST is still in the middle of its mission. It is collecting more data, looking deeper, and scanning wider patches of the sky. The story of these ancient galaxies is still unfolding. Some of them might turn out to be closer than we think. Others may reveal unexpected chemistry or strange star populations. But it is likely that many of them are exactly what they seem. They seem to be enormous galaxies that were formed far too soon. This creates a tension in cosmology. On the one hand, we have a model of the universe that works incredibly well. It works well on the large scales. On the other hand, we now have observations that seem to break that model. They break it in subtle ways. Maybe the problem is not with the theory itself. Maybe it is with the assumptions that we have made about the early universe. The JWST has given us a new tool to test our ideas against the raw facts of reality. And reality is often stranger than we expect. We thought that we had a timeline, but in those first few 100 million years, something happened. The JWST has peeled back the curtain, and behind it we are finding brilliant puzzles. These puzzles reach across time to tell us that the story of the universe is not finished. The redshift frontier. What happens when light is stretched too far? Light travels in waves. The shorter wavelengths of light like blue and ultraviolet carry more energy. They are easier to detect with visible light telescopes. But as the universe expands, the light waves from distant galaxies get stretched. They become longer and longer. Eventually, they get stretched so far that they move out of the visible range. They move into the infrared, go farther still, and they end up in microwave or even radio wavelengths. This means that if we only use regular optical telescopes, we would miss a lot. We would completely miss much of the light from the distant universe. What was once bright and blue might now be dull and red. It might even be invisible to our eyes entirely. When we observe nearby stars or galaxies, the redshift is small. But when we look at galaxies that are billions of light years away, the light has stretched. The light they have sent us has been stretched the entire time. This is why telescopes like the JWST are designed to work in the infrared. But even infrared has its limits. There comes a point where the redshift is so extreme that light is pushed out. It is pushed out of even the infrared range. At the far edge of our cosmic horizon, galaxies might exist that we cannot see. We simply cannot see them anymore because their light has shifted too far. It has shifted too far for any current telescope to detect. This redshift frontier marks the boundary between what is detectable and what is not. It is not a wall like the one caused by the CMB. It is more like a slow fade. The farther away something is, the fainter and redder it becomes, until finally it slips out of our view altogether. This makes the outer limits of the universe hard to define. Redshift also distorts how things look. A galaxy that once glowed with brilliant blue stars may now appear red and old. Its features may blur, its energy may seem lower. This can trick us into thinking a galaxy is older or colder than it really is. Astronomers have to work backwards, correcting for redshift. They try to figure out what the galaxy was truly like when the light first left it. In some cases, galaxies become so redshifted that even their hydrogen becomes invisible. This is in traditional observations. Special techniques are needed to detect this lost light. Radio telescopes can help as they pick up even longer wavelengths, but even then, some galaxies remain hidden. This stretching of light is not just a nuisance, though. Redshift is one of the main pieces of evidence that the universe is expanding. Redshift became a ruler, a way to measure space, time, and the shape of everything. Over time, astronomers have mapped the redshift of thousands, then millions of galaxies. They have built three-dimensional maps of the universe. These maps show not just where the galaxies are, but when they were. But it also reminds us that there is a limit to our vision. No matter how advanced our instruments get, redshift will always pull distant galaxies away. It will pull them away from our eyes. How dust can trick our deepest eyes. When we look at pictures from deep space telescopes like the JWST, we imagine something. We imagine that we are seeing the universe as it really is. But there is a hidden layer in almost every image. It is not made of stars or galaxies. It is dust. All across the cosmos, clouds of fine particles float between and around galaxies. These tiny bits of matter, often smaller than grains of sand, may seem harmless, but they can change the way that we see the universe in subtle and powerful ways. Cosmic dust is made up of elements like carbon, silicon, and iron. These are often formed in the atmospheres of dying stars, or they are formed in the aftermath of supernova explosions. Once they are released into space, these grains spread out and drift into vast clouds. They sometimes collect in large bands along the edges of galaxies or within nebulae. While the dust itself does not glow brightly like a star, it does interact with light. And that is where the trouble starts for astronomers. When light from a distant galaxy passes through these dust clouds, it can be absorbed. It can also be scattered. In some cases, the dust blocks visible light entirely. This creates dark patches that look like empty space. In other situations, it dims or reddens the light. This is similar to how sunlight looks redder at sunset. It looks redder when it travels through more of the Earth's atmosphere. This effect is called extinction and reddening. It means that the light reaching our telescopes has been altered. It has been filtered by the space between. This presents a serious challenge when trying to figure out how old a galaxy is, how distant a galaxy is. A faint and red galaxy might be very far away, but if there is dust in the way, it could be a much closer galaxy. It could only appear that way because its light has been dimmed and shifted. Astronomers must be extremely careful not to mistake a dusty object for a distant one, a dusty foreground object for a distant ancient one. To deal with this, astronomers use several tricks. One method is to observe the same part of the sky in different wavelengths of light. Since dust affects visible light the most but is more transparent to infrared. Switching to infrared gives a clearer view through the dust. That is one of the reasons why the JWST focuses on infrared. It is not just to see the red-shifted galaxies, but also to see through dusty regions. These regions would block a visible light telescope like the Hubble. Another method is to use models based on how dust behaves in known galaxies. By studying dust in our own galaxy and in nearby galaxies, scientists have built a library. They have built a library of dust fingerprints. These models help them to estimate how much light has been lost or changed due to dust. If a galaxy seems to be too red or faint, astronomers can use these fingerprints. They can use them to correct the data, restoring a better guess at what the galaxy looks like. But this is not a perfect science. Dust does not behave the same way everywhere. Its properties change depending on the types of stars that are nearby. They depend on the chemical makeup of the galaxy. They also depend on how the dust has been shaped by radiation or shock waves. In the early universe, the first galaxies might have had dust that was formed differently. It might have been formed differently from what we see today, or it may have existed in much larger or smaller amounts. That means that our models based on modern local galaxies might not always work well. They might not work well on galaxies that are billions of years old. This is especially important when looking at the galaxies found by the JWST, the galaxies that seem to be too big, too bright, and too old for their place in time. If dust is affecting the light from these galaxies, we might be misjudging their age. We might be misjudging their mass. A very dusty young galaxy could appear to be much older than it is. This makes it seem like it was formed too soon after the Big Bang. Or a small galaxy hidden behind a thick dust might look bigger. This is because its light is spread out. If we are not careful, we might be seeing illusions rather than real challenges to cosmology. To sort this out, astronomers try to gather as much information as possible. They look at the spectra of galaxies to search for signs of dust. Specific patterns in the light, like absorption lines or thermal emissions, can be revealing. They can reveal how much dust is present and what it is made of. The presence of glowing molecules like polycyclic aromatic hydrocarbons can also be a hint. These are known as PAHs. They can also hint at dusty regions that are full of star-forming activity. In some cases, astronomers combine data from different telescopes. They do this to get a fuller picture. For instance, they might use the JWST's infrared data to see through the dust. Then they might compare it with radio observations from telescopes like ALMA. ALMA can detect cold dust directly. These cross-checks help to confirm whether a galaxy is really as it seems. They also help to see whether dust is hiding something important. But even with these tools, there is still a lot of uncertainty. The early universe may have had types of dust that we have never seen. They would have been formed under conditions that we do not fully understand. Some theories suggest that the first stars could have created unusual types of dust. They could have created them during their deaths. If that is true, we might be underestimating or overestimating the dust content. This would be in these early galaxies. This would lead us to misunderstand what we are actually seeing. There is also the challenge of patchy dust, the uneven clumps. These clumps affect parts of a galaxy differently. This can create strange effects in the images, like parts of a galaxy appearing to be brighter or bluer than others. It can distort the apparent shape of a galaxy. This makes it look more chaotic or broken up than it actually is. Since the JWST is finding many clumpy, irregular galaxies at high redshifts, there is a chance that dust is playing a bigger role than we thought, a bigger role in how these galaxies appear. Dust acts like a cosmic mask. Understanding how to read through this mask is one of the key challenges. It is one of the key challenges facing astronomers today. As our instruments become more sensitive, dust becomes more than just a background effect, and the galaxies that we study get older and farther away. Every photon that reaches us from the edge of the visible universe has made a journey. Learning how to read that journey and correct for the obstacles is crucial. It is what allows us to turn faint blurs into real insights. Insights about how the universe was born and how it grew. When you zoom too far, the lensing problem. Gravitational lensing is one of the universe's most useful tricks, and also one of its most misleading. At a first glance, it seems like a gift. When light from a distant galaxy passes near a massive object, that light bends. This massive object could be another galaxy or a cluster of galaxies. It does not bend because of any physical barrier. It bends because gravity warps space itself. The massive object acts like a lens in a telescope. It magnifies and stretches the light that is behind it. The result is that telescopes on Earth or in space can see things they couldn't. The faint and faraway galaxies get brought into view. They are sometimes made dozens of times brighter. In many cases, these lenses are the only reason we are able to study some galaxies, some of the earliest and most distant galaxies. But this lensing does not just make the light brighter, it also distorts it. Imagine looking through a wine glass at a candle. You might see the candle appearing to be longer or split into multiple copies. You might even see it form a ring. The same happens in space. The light from background galaxies can be twisted into arcs, duplicated or smeared. It can be smeared across the sky in ways that do not look like the original source. When astronomers are studying the faint smudges of light from the edge of the universe, they often do not know if what they are looking at is the actual shape of a galaxy, or if it is just a warped view. Sometimes lensing causes galaxies to look more massive or luminous than they really are. A galaxy might appear to be unusually bright and compact. This leads researchers to think that it is an early cosmic monster, one formed just a few 100 million years after the Big Bang. But if lensing is in play, that same galaxy might actually be much smaller. It could be much fainter, and it could be from a more recent time. Without knowing how much lensing is affecting the view, scientists can overestimate. They can overestimate the galaxy's size, its age, or its star formation rate. Figuring out whether a galaxy is being lensed and by how much is not always easy. Sometimes the signs are obvious. The galaxy forms a near-perfect arc or a ring. This ring-like shape is called an Einstein ring. These are clear clues that lensing is happening. But other times the distortions are subtle. They might be hidden among other galaxies, or the lensing mass itself might be too faint to detect directly. In those cases, researchers have to rely on models. They simulate what the sky would look like with and without lensing. Then they try to match that to the real data. It is a lot like working backward from a funhouse mirror image. working backward to figure out what the original object looked like. The JWST is so powerful that it regularly captures galaxies at the very edge of visibility. These are objects that could be lensed or not. It is hard to know which. Some of the most striking early JWST images are filled with arcs and swirls, such as those from galaxy clusters like SMACS 0723. These are the visual fingerprints of lensing. These clusters are not just beautiful, they are cosmic magnifying glasses, and with them come all of the challenges. Scientists have started to build detailed lensing maps of these regions. They track the mass distribution of the galaxy clusters. They try to calculate how each portion of the sky bends light. This involves adding up the mass of every galaxy. It involves guessing how much dark matter might be sitting around them, and using equations from general relativity to estimate the bending of space. It is a lot of work, but without it, the measurements cannot be trusted. There is also the issue of strong lensing versus weak lensing. Strong lensing creates those dramatic arcs and multiple images. Weak lensing is harder to spot. It subtly stretches and distorts the shapes of background galaxies. It does this across large portions of the sky. When astronomers average out the shapes of thousands or millions of galaxies, they can detect it. They can detect this weak lensing signal and use it to learn about dark matter. They can learn about dark energy and the structure of the universe. But for individual galaxies, weak lensing adds a layer of fuzziness, a fuzziness that is hard to correct. It makes everything just a little harder to interpret. One of the surprising twists is that gravitational lensing does not just affect images, it also affects time. Light that travels around a massive object can take slightly longer to reach us. It takes longer than light that takes a straight path. This time delay can be measured in some cases, such as when we see multiple images of the same distant supernova or quasar. The light from these copies arrives at different times, sometimes days, sometimes even years apart. This strange time-warping effect can actually help astronomers. It can help them to measure the expansion rate of the universe, but again, only if the lensing is carefully modeled. Another complication comes from galaxies that are both lensed and redshifted. It can be tricky to untangle which part of that signal comes from the galaxy's actual age, which part comes from its composition, and which part from the lensing effect. Astronomers have to work through every detail. This includes whether dust or other foreground features are adding to the confusion. Some of the deepest puzzles in current astronomy might be linked to lensing. This includes the discovery of galaxies that seem to be too big, too old, or too bright. They seem to be too bright to exist so soon after the Big Bang. It is possible that some of these oddball galaxies are simply more ordinary galaxies. They are just galaxies that are caught in a lens. To manage all of this uncertainty, researchers use software that can simulate thousands of possible lensing scenarios. It can run comparisons with real telescope images. They test how different mass distributions would bend the light. They compare multiple wavelengths, and, when it is possible, they look for lensing patterns that show up in other parts of the sky. With enough time and data, they can estimate how reliable a galaxy's brightness is, or how reliable its size actually is. Even so, there is always a margin of error. Some galaxies may be misclassified. Some may look like early cosmic giants, only to turn out to be much less dramatic. And others might be overlooked altogether because they are stretched too thin, or they are blurred into shapes that do not catch the eye. That is the paradox of lensing. It helps us to see more, but it also hides and twists what we are seeing. Gravitational lensing gives us a way to peer deeper into space. But to truly understand what we are seeing, we have to unravel the distortion. We have to reverse engineer the lens. Only then can we hope to see the universe as it really was. not just as it appears through a warped glass, the oldest galaxy that was ever seen. In one of the JWST's deep field surveys, the telescope found something remarkable. A galaxy catalogued as JWST. Its light has traveled across more than 13.5 billion years of space and time. By the best measurements, this galaxy existed just 280 million years after the Big Bang. This places it among the earliest known cosmic structures. It is almost like a fossil snapshot of the universe's youth. At first glance, JWST might seem to be exactly what astronomers expected. They expected it from a galaxy of this era, a faint, distant, and extremely redshifted galaxy. But when its spectrum was examined, the data showed something that broke the simple picture. It broke the simple picture of early galaxy formation. This ancient system did not just contain hydrogen and helium, it carried the unmistakable fingerprints of heavier elements like carbon and oxygen. The implication was profound. The stars inside JWST were not the very first generation. Some of them had already lived, burned, exploded, and enriched the surrounding gas. They had enriched it with these heavier elements long before this galaxy was formed. This changes the story of the early cosmos in important ways. For one, it means that the first stars must have formed and died far earlier than we thought. These population 3 stars would have been the first to turn nuclear fusion into heavier elements. If JWST already had measurable amounts of carbon and oxygen so soon after the Big Bang, then those stars must have come and gone within a cosmic blink of an eye. It compresses the timeline of stellar birth evolution and chemical enrichment. It compresses it into a very tight window. For such a young galaxy, it appears to be surprisingly massive. This hints that star formation in the early universe may have been more rapid and efficient than the models suggest. This echoes other recent JWST findings. In the modern universe, heavy elements spread through the gas clouds gradually. This happens as generations of stars live and die. But for JWST to have detectable amounts so early, the process must have been fast. The process must have been incredibly fast and violent. Perhaps the first stars were so massive that their supernova explosions were far more energetic. They would have ejected enriched material across vast distances. Or maybe early galaxies were much more dynamic. They would have had intense bursts of star formation. These would be followed by equally intense feedback winds and radiation. This would have quickly mixed the chemical products into the interstellar medium. The detection itself relied on both the sharp imaging of the JWST and the ability to analyze light through spectroscopy. The fact that these signals were strong enough to measure across such a vast gulf of space is telling. It speaks to just how powerful the telescope is, and how lucky we are to live in an age when such measurements are possible. JWST is in some ways not just a galaxy, but a message. Its light carries information from a time when the universe was less than 2% of its current age. Every photon that we detect from it began its journey before our planet existed, before our Sun existed, and before even the Milky Way existed in its present form. Looking at this galaxy collapses basically the entire age of the universe into a single image. We are not just observing a faraway patch of the sky. We are seeing a place that has been frozen in time. Frozen since long before anything familiar in our own corner of the cosmos took shape. Before the JWST, we simply could not see this far, this clearly. Now, in just the first few years of the JWST's operation, we are rewriting history. We are rewriting the early chapters of cosmic history. JADESGSZ140 is likely not alone. Other galaxies of a similar age and composition are probably out there. They are waiting to be found. Each one of them will add another piece to the puzzle. The puzzle of how the first structures were formed, how they lived, and how they seeded the universe. They seeded the universe with the elements that would eventually make life possible. JWST GSZ140 belongs to a time that is so far removed from ours. It is hard to imagine the conditions in which it existed. Yet the fact that it already contained elements like carbon ties it to us. Carbon is the same element that makes up the backbone of all known life. This ties it to us in a subtle way. In a sense, we are seeing the distant beginnings of the chemical story. The story that would one day allow the Earth plants, animals, and people to exist. The giant eyes that will follow the JWST. Even though the JWST is the most powerful observatory ever launched into space, it is not the end. It is just the beginning of a new era of astronomy. For decades, astronomers have worked with telescopes that steadily improved over time. As soon as one telescope reaches space, scientists are already dreaming of what comes next. And today, those dreams are starting to take shape. They are taking shape in the form of even bigger, smarter, and more capable observatories. Some of them are being built on Earth, some are being prepared for space, and all of them are designed to push the limits even further than the JWST can. One of the most anticipated next-generation observatories is the Nancy Grace Roman Space Telescope. It is often just called the Roman Telescope. It is being built by NASA and is expected to launch near the end of this decade. At first glance, the Roman might not seem to be all that different from the Hubble. In fact, it has a similar mirror size, about 2.4 meters wide. By comparison, the JWST's mirror is 6.5 meters wide. But what sets the Roman apart is how much sky it can see at once. The Hubble and the JWST both focus on small, detailed patches of space. The Roman, by contrast, has a field of view that is hundreds of times larger. It can scan vast regions of the sky in a single shot. It is like going from a microscope to a wide-angle lens. This wide view is a game changer. The Roman will be able to survey huge numbers of galaxies, stars, and planetary systems. It will be able to do this all at once. That means that it can find patterns that the JWST cannot. While the JWST might zoom in on a few early galaxies in detail, the Roman could map entire populations of galaxies across cosmic time. This will help us to understand how structure was formed in the universe on a large scale. It will also be a powerful tool for discovering exoplanets. It will use a technique called microlensing to spot distant worlds that are otherwise invisible. But the Roman is not alone. Back on Earth, astronomers are preparing telescopes that are so large and so complex. They would have seemed like science fiction just a few decades ago. One of these is the Extremely Large Telescope, or ELT. It is under construction in Chile. The name might sound a little on the nose, but it is accurate. This telescope will have a mirror that is nearly 40 meters across. It will be made up of almost 800 hexagonal segments working together. They will work as one enormous surface. That is more than 5 times the size of the JWST's mirror, and it will gather more than 15 times the light. Because it is on Earth, the ELT has to deal with the atmosphere. The atmosphere blurs images and distorts light, but modern technology can correct for this. The ELT will use adaptive optics, a system of lasers and mirrors that adjust in real time to cancel out the blurring that is caused by Earth's air. This gives it the ability to produce incredibly sharp images. In some cases, even better than the JWST's. It will not be able to see in quite the same deep infrared range that the JWST does, but in the near-infrared and visible bands, it will be unmatched. With instruments designed to study everything from exoplanets to dark matter, the ELT is meant to be a true general-purpose observatory. It will be able to zoom in on planets around other stars. It will be able to analyze their atmospheres, searching for chemicals like oxygen and methane that could be signs of life. It will also be able to look deep into space and time. It will study the light from ancient galaxies formed soon after the Big Bang. The goal is to connect the big picture, how the universe evolved, with the fine details of what individual stars and planets are made of. Another powerful eye that is being built is the 30-meter telescope, or TMT. It is also planned for the southern hemisphere. Like the ELT, the TMT will have an enormous segmented mirror, in this case 30 meters wide. It will also use adaptive optics and focus on similar goals. It will help astronomers to study distant galaxies, black holes, and alien worlds. Having multiple giant telescopes on Earth is not a redundancy. It is a reinforcement. Different locations offer different views of the sky. They offer different observing conditions and allow for around-the-clock science. This happens as the Earth rotates. Together, the ELT, the TMT, and others form a network of giant eyes. These eyes will scan the skies from the ground. But what about space? Even with all of the technology on Earth, nothing compares to observing from above the atmosphere. That is why astronomers are already thinking about the next flagship space telescope, the next one after the JWST. One of the top candidates is called LUVOIR. It stands for the Large UV, Optical Infrared Surveyor. LUVOIR is still in the planning stages, but its proposed designs are ambitious. The smallest version would have an 8-meter mirror. This is already much bigger than the Hubble or the Roman, and the larger version could be 15 meters wide, more than double the size of the JWST. LUVOIR would be a true all-in-one machine. It would study planets, stars, galaxies, and the structure of the universe. It would look for biosignatures, gases that hint at life in the atmospheres of Earth-like planets. It would map the structure of the Milky Way in stunning detail. Its ultraviolet instruments would detect clues that other telescopes cannot see, and its sharp vision would allow it to study exoplanets directly. It would separate their faint light from the glare of their stars. Another proposed telescope is HabEx. This is short for the Habitable Exoplanet Observatory. As the name suggests, it is designed with one primary goal in mind: to find habitable worlds. Unlike LUVOIR, which is broad in scope, HabEx is more focused. It would specialize in studying stars that are like our Sun. It would search for planets that orbit in the right zone, not too hot, not too cold, where liquid water could exist. HabEx would carry a special companion, a starshade, a giant flower-shaped shield that would fly thousands of kilometers ahead of the telescope. It would block out starlight and let the telescope see the much fainter planets nearby. All of these future telescopes are a part of a larger journey. Astronomy is a chain of tools, each one building on the last. The JWST is giving us our first sharp look at the early universe. The Roman will zoom out and show us how widespread those strange galaxies are. The ELT and the TMT will zoom in again, studying them in detail. LUVOIR or HabEx could then tie those details back to the question of life and structure. Each telescope answers questions and raises new ones. What is clear is that we are not stopping. The more we see, the more we want to see. And now that we have gotten our first real glimpse of what lies at the edge of everything, we are building bigger and better tools to go even further. Just as the JWST was a leap beyond the Hubble, the next generation will leap beyond the JWST. And if the universe has taught us anything so far, it is that every time we look deeper, we find something stranger and more beautiful than we expected. The orbiting monoliths. Could we build a telescope that is bigger than the Earth? The JWST, as incredible as it is, uses a mirror that is just over 6 meters wide. That size limits how much light it can collect and how detailed its images can be. It is like trying to take a picture of a grain of sand from across a stadium. You are using a small handheld camera, but if you make the mirror wider, much wider, then your picture gets clearer. You can see the finer features, the fainter objects, and the smaller things that are farther away. The problem is that we cannot just build a mirror the size of the Earth. We cannot launch it into space. It is not remotely feasible with today's rockets. And even if it were, keeping something that large, stable, and pointed would be nearly impossible. That is where a clever trick comes in, a trick called interferometry. Interferometry is the idea of combining multiple smaller telescopes. They are spread out over a great distance so that they act like one giant telescope. Instead of one big eye, you use many small ones working together. If you place them far apart and combine their signals correctly, you get the same sharpness. You get the same sharpness as if you had one big mirror stretching between them. We already use this trick on Earth. Radio telescopes like those in the Very Large Array in New Mexico work this way. The network that helped to take the first picture of a black hole also works this way. The Event Horizon Telescope. They are built from dishes that are spaced miles or even continents apart. But doing this in space would be an entirely new level. Imagine putting a telescope on one side of the moon's orbit and another on the opposite side, or putting dozens of telescopes in a line stretching across Earth's orbit. Suddenly, you are seeing details that no telescope today could even dream of. One of the most talked about future missions using this method is LIFE. It is a project called the Large Interferometer for Exoplanets. The idea is to launch multiple infrared telescopes into space and fly them in formation. By carefully syncing their observations, scientists could cancel out the light from stars. They could isolate the much dimmer light of the orbiting planets. It would be like turning down a spotlight just enough to see the firefly next to it. That kind of clarity is more than just nice, it is necessary. If we want to study the planets around other stars, we need to see them as real places. We need to see them not just as tiny points of light. We need to see them as places where we could search for clouds or oceans. We could search for signs of life in their air. Interferometry could allow us to see those details for worlds dozens of light years away. Another wild concept is something called the hypertelescope. Instead of one mirror or dish, it would be an array of mirrors flying in space. They would fly in a precise pattern. These mirrors would not form one surface, but would work together. They would work like the scattered pieces of one huge invisible lens. The idea was first suggested by the French astronomer Antoine Labarre. In theory, it could produce images that are sharp enough to see continents on alien planets. The engineering challenges are massive, keeping everything aligned while floating in space, dealing with vibrations, shielding from solar radiation, and managing fuel and power. But the concept keeps on drawing attention because the payoff is so big. There is also the orbiting rainbows idea, not an official name but a poetic one. It comes from a concept called star shades. A giant flower-shaped shield is flown thousands of kilometers in front of a telescope. It blocks the light of a star. With that glare out of the way, the telescope behind it can clearly see the planets. Pairing this method with an interferometer could give us both light filtering and resolution. It would give us the resolution needed to directly image Earth-like planets, and maybe even their weather systems. All of these future tools share something in common. They are more than just bigger versions of the old telescopes. They are using entirely new methods of seeing. They treat space itself as a part of the instrument. They use formation flying, precise timing, and optical tricks to build virtual telescopes. Virtual telescopes that are wider than any structure that we could ever build physically. And some of the designs go even further. There are papers exploring the idea of using swarms of microsatellites. Each one would be the size of a toaster. They would work together in tight coordination to form reconfigurable telescopes. If one satellite drifts, the others adjust. If a section needs a repair, a few satellites can be replaced. This makes the system flexible, expandable, and more resilient than any single telescope. There is also a growing interest in using the Moon itself as a base for giant telescopes. The far side of the Moon is naturally shielded from Earth's radio noise. This makes it a perfect quiet zone for building a huge radio telescope, maybe even one that stretches across a crater. If we ever get a lunar base up and running, this could be one of its first scientific missions. Building on solid ground rather than floating in space would bring some advantages. This would be in terms of stability and maintenance. But whether it is in space on the Moon or around the Sun, all these concepts point in the same direction. We are hitting the limits of what one telescope can do alone. To go further, to see finer, to explore deeper, we have to start thinking bigger. That means working across distances, combining instruments, and treating space itself as a part of the machine. There is something poetic about that. It means that our tools for looking outward are starting to resemble the universe. They are starting to resemble the universe that they are trying to understand, large, distributed, and full of pieces working together. A telescope by a star, the Solar Gravitational Lens Project. Far out in the solar system lies a strange and powerful region of space. This is more than 500 times the distance between the Earth and the Sun, taking advantage of the fact that the Sun can gravitationally lens light. This bending can be used to construct a gigantic natural telescope. This idea is known as the Solar Gravitational Lens Mission. While it sounds like something from science fiction, it is rooted in real physics. It is also rooted in actual mission design plans. The Sun's gravitational field bends light coming from behind it. It curves it inward toward a central axis that stretches far into space. If you place a camera or a sensor along that axis at just the right distance, this distance starts around 550 astronomical units, or an AU. Light from a distant object behind the Sun will focus there. It will form a thin, magnified ring. With the right equipment, it would be possible to collect that light. We could reconstruct an image of whatever object lies behind it. The scale of magnification is staggering. The Sun's gravity does not just bend light a little, it warps it in a way that theoretically allows for up to 1 trillion-fold magnification. That is enough to image the surface of an exoplanet tens of light years away. We could see it in kilometer-scale detail. Instead of just detecting a tiny dot of light and measuring its spectrum, we could potentially build an actual image of the planet, the clouds, the oceans, the continents, and maybe even the signs of technology or vegetation if they are there. The project has been described by some scientists as the most powerful telescope humanity could ever build. We could build it without building anything big. We would just place a small spacecraft in the right place. The technical challenges are huge. To get to 550 AU would take decades with current propulsion technology. The Voyager 1 spacecraft, launched in 1977, is the most distant human-made object. It has only just passed 160 AU after nearly 50 years of travel. Getting to the focal point of the solar gravitational lens would require new methods. We would need new methods to reach the necessary speed. The mission would also require extremely stable positioning. The spacecraft would need to hover in a region barely tens of kilometers wide. It would have to track a target light years away. It would also have to block the Sun's direct light from overwhelming the faint signal. Another major challenge is the distortion of the image. The light that reaches the solar gravitational lens does not form a normal flat picture. Instead, it is warped into a ring. To reconstruct a proper image, a spacecraft would have to move sideways across that ring. It would slowly collect data from different angles. Then it would use advanced algorithms to reverse the distortion and form a coherent picture. It is not like snapping a photo with a camera. It is more like slowly reading the grooves of a vinyl record one point at a time, then reconstructing the music from the shape of those grooves. Despite these hurdles, teams from NASA and other institutions have tried to map out the requirements. They have tried to map out what a solar gravitational lens mission would require. A conceptual study called FOCAL has already laid out the early mission design. There are ideas to pre-launch multiple probes that work together, or as backups. They might use small lightweight materials and carry only essential instruments. Once they are far enough from the Sun, the spacecraft could deploy small shielding disks. They would block solar glare and begin searching for target alignments. The kind of targets they are interested in are not random stars or galaxies. They are specific exoplanets that have already been identified by missions like Kepler or TESS. These are planets that orbit in the habitable zone of their stars. This is where telescopes like the JWST have picked up potential signs of atmospheres, signs of water, or interesting chemicals. The idea is to choose just one or two of these planets and design a long-term mission. A mission to fly out to the gravitational lensing point and observe them directly. That way, instead of guessing what is happening on these worlds, we could actually see them. Some versions of the mission concept propose launching by mid-century, perhaps as a part of a larger push toward deep space exploration. If propulsion technology advances fast enough, such as using solar sails powered by lasers, the time to reach 550 AU could be brought down to under 20 years. That would make the mission more feasible within a human lifetime. The scientists involved in the early studies say the science return would be unmatched. It would be a chance to directly observe other Earth-like worlds. We could possibly even look for continents, oceans, storms, or city lights. But even beyond the planets, a solar gravitational lens mission could be used for a wide range of science. It could be used for a wide range of deep space science. Its ability to collect light over vast distances could let it peer into ancient parts of the universe. It could detect dim galaxies or even look for signs of cosmic background ripples. It is like unlocking a tool that nature has already built. We just need to get into the right place to use it. Some compare the project to the idea of a cosmic microscope. Instead of building a giant optical system on Earth or in orbit, we use space-time. We use the curvature of space-time itself, created by the Sun's gravity, to do the focusing. In a way, it is the ultimate lens, one that does not wear down, break, or need maintenance. Of course, as with all large space projects, the road from concept to reality is long. Budget, political interest, and competing priorities may slow things down. And there are still unknowns like how much solar interference will affect the signals, or how easily a spacecraft can hold a position so far from the Sun's warmth and power. But the growing interest in exoplanets gives the idea momentum. This is especially true for those that might resemble Earth. With each passing decade, the desire to actually see other worlds becomes stronger. Not just to detect them, but to look at them. Instead of always building more hardware, sometimes we just need to understand how nature works. We need to find clever ways to use it. Gravity, light, and distance, these forces already shape the universe. Now, perhaps, they can help us to explore it more clearly than ever before. Putting a telescope at 550 AU, reaching 550 AU away from the Earth, is not just an engineering challenge. It is a stretch of the imagination. That distance is far beyond the Kuiper Belt, and even beyond the Oort cloud's inner edge. It is a place where sunlight is just a dim glow, where communication signals take more than 3 days to travel one way. Getting there and making it work pushes us to the edge of everything we know. It pushes us to the edge of what we know about spaceflight. If we sent a Voyager-style spacecraft today, it would take around 150 years. It would take that long to get to 550 AU. If we want to build something useful in a human lifetime, we need to go much faster. Solar sails are large, thin sheets that catch the pressure of sunlight. Just like wind in a sailboat, they push a spacecraft forward. The closer the sail gets to the sun, the stronger the push. Some proposals suggest diving very close to the sun, letting the sunlight give a powerful shove, and using that boost to fling the spacecraft outward. With the right materials and timing, some simulations show we could reach it. We could reach 550 AU in 25 to 30 years. Another possibility is electric propulsion, the ion drives. They slowly but steadily build up speed over the years. These engines do not give the kind of instant push a rocket does, but they are much more efficient. The NASA's Dawn mission and the European Space Agency's Bepi Colombo both use this system. Scaling it up for deep space travel would require careful planning. It would require a lot of power and a spacecraft that could stay functional for decades. Whichever method is chosen, the spacecraft will have to be tough. At 550 AU, space is harsh and cold. The solar panels that we usually rely on will not work well. This is because sunlight is too weak. Instead, the spacecraft would need to carry its own power. It would probably use a radioisotope thermoelectric generator. This is like the one on the Voyager or the Mars rovers, but even those decay over time, so every watt of energy has to be used wisely. The systems must be highly efficient, and the entire mission has to be designed for extreme endurance. Then there is the question of navigation. The spacecraft has to arrive in a very precise location. The gravitational lens effect only works if the object, the sun, and the spacecraft are perfectly lined up. That means that we need incredibly accurate maps and powerful navigation software. We would also need mid-course correction systems that can work over decades. Once the spacecraft gets to the lensing point, it cannot stop. It has to keep on moving further out. This is because the focal region of the sun's gravity is not a point, but a line. It is a line that stretches out behind the sun. As it moves, it would scan along that line, collecting different pieces of the target image. Scientists believe that with the right instruments, it could eventually combine these slices. It could combine them into an incredibly detailed picture. That brings up another major challenge: data. Special software would be needed to untangle these patterns and turn them into useful pictures. A spacecraft that is that far away would have to send its data back. It would have to send it back across 550 AU, more than 80 billion kilometers. A message would take over 3 days to reach the Earth. And because of the distance, it would be incredibly faint. To catch it, we would need very large antennas on Earth, or perhaps even a network of receivers working together. That is a challenge of its own, but it is one that deep space missions have slowly been preparing us for. A mission like this takes decades. That requires a different mindset, one that is focused on a legacy and the long arc of discovery. It is the kind of thinking that built cathedrals or planted trees. The shade of these trees would only be enjoyed by future generations. It is hard to justify in a world focused on short-term rewards, but space exploration has always been about patience. A telescope that is made of nothing but light. Unlike normal glass lenses which bend light through their shape and thickness, diffractive optics works by using extremely fine patterns etched onto a surface. These patterns manipulate the path of incoming light. They take advantage of the way that light waves interact. In some designs, these patterns could be printed onto ultra-thin films. They could be as thin as a soap bubble. They could be launched into space tightly folded and then unfurled like a giant sail. Once expanded, they would act as lenses that could focus light. They could focus light from distant galaxies and exoplanets, but they would weigh a fraction of what a mirror or a lens would. The benefit here is clear. When launching things into space, weight is expensive. Every gram adds to the fuel and the cost. The mirrors, like those used in the Hubble or the JWST, are heavy. They need a lot of structural support to hold them in place. Diffractive optics, on the other hand, could float almost freely. They could be shaped and stabilized by the slightest push, sometimes even by light itself. This leads to another fascinating idea, using lasers or sunlight to form or control the shape of the lens. This is known as photonic engineering, and it is still in the very early stages, but the potential is enormous. There is a related concept that goes even further: optical metasurfaces. These are surfaces that are engineered at the level of atoms. They have structures that are so small that they can control the phase and direction of light. They can do so in precise ways. With metasurfaces, you do not even need a curved lens to bend light. You can do it with a flat surface, one that is carefully designed to make light behave as if it had passed through a traditional lens. This means that the future of telescopes might involve flat sheets of material. These sheets can act like giant focusing eyes without the bulk or complexity of traditional designs. In space, these sheets could be unfolded like origami, or they could be printed directly by machines that are already in orbit. Then, there are the ideas that push the concept of light-based optics to its most extreme version. These are telescopes that use laser-formed lenses. Imagine firing a set of lasers into empty space in just the right configuration. The crossing beams could create a lens out of nothing, just an area in space where light gets bent in a certain way. This is not something that we can build yet, but the basic physics is not impossible. Under the right conditions, light can shape the space that it passes through, especially if it is moving through a medium like a plasma or even atoms that are cooled to a near absolute zero. In the far future, this could let us build a telescope that does not need any solid parts. It would just need fields of energy that are shaped and aimed from a distance. But even without going that far, we are already seeing versions of this idea in development. For instance, one proposal was called MOIA. It stood for the Membrane Optical Imager for Real-Time Exploitation. It was designed by DARPA as a kind of space-based telescope made of folding membranes. It would use a series of lightweight diffractive lenses to collect and focus light. It would create high-resolution images of the Earth or deep space. While MOIA has not flown yet, it shows how this approach could work. Other versions involve inflatable structures. Think of giant space balloons that act like lenses or mirrors when shaped correctly. These could be built on the ground, launched, folded up and inflated once in orbit. They would stretch out into enormous telescopic arrays. One of the big advantages of using these light-based or membrane-based designs is size. With solid mirrors, you eventually run into limits. How big can you make it before it breaks under its own weight, or before it becomes too difficult to launch? With light materials or optics formed by light itself, you can dream much bigger. Telescopes with collecting areas the size of football fields or even football stadiums. These could detect fainter signals from farther away than anything we have ever built. Signals from the first stars, or perhaps from alien civilizations. Some designs imagine fleets of these structures flying in formation. They would act together like one massive lens. Interferometry is used in radio astronomy. But in the future, it might work with optical or infrared light too. It would give us a kind of artificial eye, the size of the moon's orbit. Still, these dreams come with challenges. Making sure a lightweight lens keeps its shape in space is not easy. Vibrations, temperature changes, and even tiny impacts from micrometeoroids could shift or damage it. Controlling something made of light or an ultra-thin material requires precise guidance systems. These sometimes involve tiny thrusters or magnetic fields. And interpreting the data from these new kinds of telescopes would take software that can handle strange distortions or signals unlike anything we have seen before. There is also the question of how to aim a telescope that is made of flexible material, or one made of laser fields. Traditional telescopes move with motors and gears, but something that bends like a sail or changes with energy might need a new way of pointing. Some researchers suggest using electric fields to tweak the shape of the lens, like muscles flexing in response to a signal. Others imagine adjusting the power and angle of laser beams to shift the whole focus, like steering with sunlight. All of this suggests a very different future for astronomy, one where we do not just build bigger telescopes, but stranger ones, instruments that look more like sails, membranes, or light sculptures. They would look more like that than anything we would call a telescope today. But their goal remains the same: to gather the faint signals from across the universe, and to bring us closer to the answers about where we come from. As we begin to master the strange behavior of light and learn how to bend it without glass or mirrors, we open a new era in our view of the cosmos, an era where our telescopes may become as invisible as the mysteries they seek to reveal. The observable universe is not the whole universe. Some scientists have tried to estimate how much more of the universe there might be, how much more there is beyond the observable part. Depending on the models, it could be hundreds, thousands, or even trillions of times larger. It could be larger than what we can see. If the universe is infinite, then anything that can happen might happen, not just once, but many times. There could be other Earths, other galaxies that look just like ours, and even copies of you who are reading this right now. These are the logical consequences of certain cosmological models. They are extreme, but they follow the math. Others are more cautious. They say that we cannot assume what we cannot observe. The universe might be infinite, or it might be shaped in a way we have not yet imagined. A curve that is so gentle that it only looks flat to us. Maybe it loops back on itself over vast distances, like a giant sphere or a torus. If that is the case, then perhaps the universe is finite but unbounded. You could fly in a straight line forever and end up back where you started. You would never hit an edge. But even if that is true, the size of the loop would be far larger than our bubble, our observable bubble. The observable universe is our window, but it is not the whole house. It is not even the whole street. We live inside a patch of the cosmos that we have learned to map in incredible detail. Yet beyond it lies an ocean of uncertainty. Still, humans are not good at accepting boundaries. Every time that we run into one, we try to push past it. That is what telescopes have always done, not just to magnify, but to reveal what was once thought to be unreachable. So now, some scientists are looking for ways to stretch the edge again, not by moving the limit of the observable universe, which we cannot do, but by using clever tricks like quantum measurements or strange statistical methods. These might hint at what lies beyond. There is also another approach, looking for echoes. If something big happened in the far-off universe, it might leave a trace, like a strange pattern in the CMB. It might leave a trace inside our visible patch. Some cosmologists think that these could be signs of other universes, or different domains in a larger multiverse. If such a trace were found, it would not show us what is out there, but it would suggest that an out there exists in a real and active way. All of this leaves us in a strange place. We are surrounded by more questions than answers. We can map galaxies, measure redshifts, and watch light curving around clusters. We can watch it fading into a background radiation, but we cannot see beyond the cosmic curtain. We know that the play does not end at the edge of the stage, but we do not know what scenes are unfolding off-screen. Could wormholes be the cosmic telescopes? A wormhole is a theoretical structure in space-time. It is often imagined as a shortcut between two very distant places. Instead of traveling across billions of light-years through space, you could jump through a wormhole and arrive almost instantly on the other side. In sci-fi, wormholes are used to travel across the galaxy in a second. But in real physics, they are an open question. They could exist, but we have never seen one. We do not know if they can be made stable enough to use. Still, they show up in the solutions to Einstein's equations. That means that, at least mathematically, they are allowed by general relativity. The big challenge is figuring out whether nature actually builds them, and if it does, whether anything could pass through safely. But let's say for the sake of argument that wormholes are real and usable. Could we use one to see something that we otherwise never could? In normal space, we are stuck looking only as far as light has had time to travel. That is why we cannot see beyond the edge of the observable universe. That is where wormholes enter the picture in an interesting way. Imagine a wormhole whose opening lies somewhere near the Earth. Now suppose that the other end of that wormhole opens somewhere far beyond our observable universe. If the wormhole is stable and if we could send light through it, or receive light from the far end, then we might be able to see what lies beyond the cosmic horizon. In theory, we could peer into a region of space that by every other method is out of reach. The wormhole would act like a telescope, but one that does not rely on light traveling the normal path through space. Some physicists have asked if wormholes exist, could light pass through them, and if it can, then what would the image look like when it comes out the other side? Turns out that this question leads to all kinds of new puzzles. Light that bends through a wormhole does not follow a straight path. Its journey is curved and strange. That means that the image that we see might be warped or compressed. The shapes could be distorted, the colors might be shifted, and even time itself might appear to behave differently. This would depend on how the wormhole curves space. Some simulations have tried to model what you would see when looking through a wormhole. In most of them, the image that you get is circular. It is like looking through a peephole. Around the edges, the view bends, and you can sometimes see behind and around objects. This is because light is wrapping through the tunnel in multiple ways. In the center, you might see a clear view of a world that lies unimaginably far away. If that faraway place was a galaxy, you could see it as it is now, not just how it looked billions of years ago. You could bypass the normal delay that light has when traveling through space. That alone would be incredible. One of the major limits of cosmology today is that we are always looking into the past. But if wormholes let us look across space without that time delay, we might finally get a look at galaxies not as they were but as they are right now. It gets even more interesting when you consider the possibility of peering into a separate region, a completely separate region of the universe, a place that was formed with a different arrangement of matter, with different galaxies and maybe even different physical properties. If the wormhole's other end opened into a part of the universe that had different conditions, then we might see what the cosmos is like beyond our cosmic bubble. And that could help to answer deep questions about whether the universe is truly uniform. Is it uniform on the largest scales, or whether we just live in a tiny patch that looks smooth and regular? There are also more speculative ideas. Some theories of the universe suggest that other bubble universes might exist. These would be parallel regions of space, with different constants, particles, or even laws of physics. If wormholes could somehow connect not just distant places in our own universe, but places across these cosmic domains, then the telescope becomes something much stranger. It would no longer be just a window across space. It would be a window across possible realities. That is an enormous leap, and it depends on whether our universe allows for those structures. Right now, we just do not know. But even sticking to our own universe, the use of wormholes as observational tools would be a big shift. It would mark a complete shift in how we do astronomy. All of our current instruments rely on collecting light that has traveled across space. With wormholes, light could take a shortcut. We might see things out of sequence. We might look at events that have not yet happened from our perspective. This would raise questions about causality, about time, and about how information travels. In some versions of the theory, wormholes can even act like time machines. If that is true, then looking through one might not just show us a distant place. It might show us a different moment in time, possibly the future or the past. Wormholes are tricky to handle mathematically. Some of them require forms of exotic matter to stay open. These are types of material with negative energy which have not been observed in nature. Others close too quickly or collapse when anything tries to pass through. But not all of the models are doomed. Some of them suggest that wormholes could exist at the quantum scales, or that they might emerge under certain extreme conditions, like near black holes or in the early universe. One idea that is still very new is that entangled particles might be connected, the kind that show up in quantum experiments. They might be connected by tiny wormholes. If this is true, that could mean there is a deeper relationship between space information and connectivity. In that case, wormholes would not just be weird tunnels in space, they might be a basic feature of how the universe is built. We are already dreaming of gravitational lenses, interferometry, and other tools that stretch our reach. But if wormholes are real, and if we can figure out how to use them safely, they could change everything. They could turn the cosmos into something that is more connected, not just in space, but in time, and even between worlds that we cannot currently reach. The neutrino eyes. The neutrinos are among the strangest particles in the universe. They are almost massless, they carry no electric charge, and they pass through normal matter as if it is not there. At any given moment, trillions of them are streaming through your body. They are mostly coming from the sun. They do this without you feeling or noticing a thing. They are so elusive that the name ghost particle has become almost standard. It is standard in describing them. But while this might make them sound unhelpful for astronomy, the truth is the exact opposite. In fact, their very ability to slip through matter without scattering makes them perfect messengers. They are perfect messengers from places that light itself cannot reach. Beyond the CMB, in terms of photons, the universe is hidden from view. But neutrinos, which are electrically neutral and incredibly non-interactive, could pass through. They could pass through that hot plasma almost unhindered. If we could detect them well enough, they could let us look back. They could let us look back to the very first seconds after the Big Bang. These are eras of cosmic history that are invisible to light. Neutrinos already have a long history in astronomy. We have used them to study the sun's nuclear reactions directly. This has confirmed that it produces its energy through fusion. We have detected bursts of neutrinos from supernova explosions. This has given us a way to watch the inner collapse of a dying star. We can see this before the shock wave becomes visible in light. But these are just hints of what could be possible. Imagine if our telescopes were sensitive not just to photons, but also to the vast numbers of neutrinos arriving from across the universe. In a way, it would be like giving astronomy an entirely new sense, one that could pierce through opaque walls and reveal hidden events. The biggest obstacle is that neutrinos interact so rarely with matter, we need extreme measures to detect them. Current neutrino observatories like the IceCube Neutrino Observatory rely on large volumes. It is buried deep in the Antarctic ice. It relies on cubic kilometers of detection medium just to capture a few events. A neutrino will only very occasionally collide with an atomic nucleus. This produces a flash of light or a trail of secondary particles that can be recorded. For neutrino astronomy to open the truly ancient chapters of the universe, we would need detectors that are many times larger and more sensitive than anything that we have today. If such a technology existed, it could let us see the cosmic neutrino background. This is the neutrino counterpart to the CMB, but it was formed even earlier. These relic neutrinos were released when the universe was less than 1 second old. This is almost unimaginably close to the moment of creation. They carry information about the extreme conditions at that time. This includes the density, temperature, and composition of the young cosmos. Detecting the cosmic neutrino background would be like finding fingerprints, the fingerprints of the very laws of physics operating at their most extreme. It could reveal whether the universe expanded smoothly from the Big Bang, or if it passed through exotic transitions, such as brief phases dominated by strange forms of matter or energy. It could even hint at entirely new particles or interactions that we have never seen in a laboratory. Even without going that far back in time, neutrino eyes could transform our view. It could transform our view of cosmic events. For example, the earliest generations of stars and galaxies were often enshrouded in dense gas. These materials can block most wavelengths of light, but not neutrinos. We could watch star formation happening inside thick clouds. We could see it long before their first light could escape. We could witness black holes forming in the cores of collapsing stars. We could see the moment of their birth instead of the delayed fireworks of their aftermath. We could even monitor the collisions of neutron stars and black holes from deep within. We could trace the processes that generate heavy elements like gold and platinum. Neutrino astronomy could also help to answer one of the deepest puzzles in physics: why there is more matter than antimatter in the universe. The very early cosmos should have produced both of them in equal amounts. They would have annihilated each other, leaving behind nothing but radiation. Yet here we are living in a universe that is made almost entirely of matter. Some theories suggest that subtle differences in how neutrinos and antineutrinos behave could have tipped the balance. This would have happened in the first fractions of a second. To test this, we would need to capture the neutrino signals from that era. We would need to analyze them in detail. From a practical standpoint, building neutrino eyes that can see the entire universe is a monumental challenge. It is a monumental engineering challenge. We would need detection volumes that are perhaps the size of small planets. Or we would need innovative new materials that can dramatically boost interaction rates. We would need to do this without requiring impossible amounts of matter. Some researchers imagine using natural planetary bodies as detectors. They would read out the faint signals caused by neutrino collisions deep underground. The day that we open these neutrino eyes, our idea of the beginning of the universe might change forever. We might find that the first second after the Big Bang was far more eventful than we imagined. It could have been full of exotic phenomena that light will never be able to tell us about. Or we might discover that our current models were wrong in fundamental ways. This would force a rewrite of cosmic history. Either way, the ghost particles that slip silently through us every second could one day become our most important guides. They could guide us to understanding where everything began, seeing with something other than light. There are places that light cannot go, or if it does, it gets so bent, scattered, or absorbed that it doesn't tell us much. This is by the time that it reaches us. But the universe does not speak in light alone. There are other messengers, and over the last few decades, we have learned how to listen to them. It was predicted by Einstein over 100 years ago. Gravitational waves are created when massive objects move in extreme ways. Imagine two black holes spiraling into each other and merging. The force of that collision does not just send out energy. It shakes space-time like a pond that is hit by a stone. Those ripples travel outward at the speed of light, and when they reach the Earth, they are so faint, they stretch and compress space by less than the width of an atom. For decades, these waves were purely theoretical. No one thought that they could ever be measured. But in 2015, scientists using the LIGO Observatory did just that. They detected a tiny tremor in space. It was caused by the collision of two black holes more than 1 billion light-years away. It was the first time in history that humanity had observed the universe in a new way, not through light, but through gravity itself. Gravitational waves have opened a new window on the cosmos. They do not get blocked by dust or clouds. They do not scatter. They carry information about the most violent and mysterious events in the universe. Things like neutron star crashes, black hole merges, and possibly even echoes from the beginning of time. And as the detectors become more sensitive, we will be able to hear fainter and more distant signals. These are not just new observations, they are a completely different kind of vision. Together, neutrinos and gravitational waves are helping to build a new kind of astronomy. It is sometimes called multi-messenger astronomy. The idea is to look at the universe with as many senses as possible. Use light, yes, but also particles, gravity, and anything else that can carry a message. When a single event is seen in both light and gravitational waves, it gives us a fuller picture. Or when it is seen in light and neutrinos. It is like watching a silent movie versus hearing the sound too. There may be other messengers waiting to be discovered. Some scientists think that there could be particles that are even more elusive than neutrinos, ones that barely interact with anything at all, but still carry energy and information. Others imagine strange fields or forces that could ripple across the cosmos. The history of science suggests that every time we build a new kind of instrument, we find something unexpected. Entire worlds of knowledge can open up from a single breakthrough. There is also dark matter. Its gravity holds galaxies together, bends light, and affects how the universe expands. If we could find a way to detect the particles of dark matter directly, not just through their gravitational pull, but through some kind of new interaction, it could change everything. It would be like discovering a new sense. It is easy to forget that what we call seeing is just one way of knowing. It works well on Earth, where light reflects off trees, water, people, and animals. But space is not the Earth. If we want to understand the universe in full, we need to think beyond the eye. We need to think even beyond the telescope. The cosmos has many voices. Is there a way to see faster than light? Is there any way to cheat the speed of light? Could we observe something without having to wait for its light to crawl all the way to us? One of the oldest ideas proposed in physics to break the speed of light is the tachyon, a hypothetical particle that always moves faster than light. Tachyons, if they existed, would never be able to slow down below light speed. They would be the opposite of everything that we know. According to special relativity, they would carry an imaginary mass. Not imaginary as in fake, but imaginary as in numbers involving the square root of a negative one. Mathematically, that does not break any rules, but it is a strange way to describe something that is real. For decades, physicists have searched for any trace of tachyons. They have searched in cosmic rays or particle accelerator data. So far, there is nothing. Still, the idea of faster-than-light communication or observation will not go away. This is because the possibilities are so huge. Imagine if we had a way to detect changes in a galaxy the moment they happened. No delay and no time lag. It would be like turning the universe into a live feed. You could monitor a supernova in real time, or even watch how a black hole's surroundings change as matter spirals in. But for any of this to happen, we would need a signal that could travel faster than light. Not just a particle, but a method of moving information. And that is where the real problem lies. In physics, sending information faster than light usually leads to paradoxes. If you could send a message that arrives before it was sent, cause and effect get twisted. You could warn yourself of something before it happens, or prevent something that caused the message to be sent in the first place. This opens the door to logical contradictions, the kind that break the foundations of our understanding of time. Many physicists argue that this is why faster-than-light communication is impossible. But there are ways to get around the strict rules, at least in theory. One of the ideas involves quantum entanglement, the behavior that Einstein once described as spooky action at a distance. When two particles are entangled, measuring one of them instantly affects the other. This happens no matter how far apart they are. This seems like it could be used to send messages faster than light, but in reality it cannot. You cannot control the outcome of the measurement. This means that you cannot use it to transmit information. The link is real, but it is more like a shared randomness than a signal. Another idea comes from the world of curved space-time. If space itself can expand faster than light, which it did during the early inflationary period, after the Big Bang, then maybe we can use that feature in reverse. What if you could create a kind of bubble where space contracts in front of you and expands behind you? This is the idea behind the Alcubierre drive, which is sometimes called a warp drive. It does not move faster than light in the normal sense. Instead, it moves by distorting space itself. You would not be moving through space faster than light. Space itself would be doing the moving. If such a drive were possible, then a telescope mounted on it could, in theory, reach places. It could reach them far faster than a beam of light ever could. You could send it across thousands of light years and get it to the destination in a human lifetime. It could collect data up close, then use the same drive to return. But this too is still just a theory. The Alcubierre drive requires negative energy, something that we do not know how to create or contain. And even if we could, building a stable warp bubble is a challenge. No one knows how to tackle it. There is also the idea of hypothetical particles or fields that we have not discovered yet. Things that might exist outside the standard model of physics. If the universe has more dimensions than we can perceive, then it is possible. Some form of energy or signal could move through those hidden dimensions. It could do so in a way that bypasses our speed limit. It is like thinking in 2 dimensions and trying to imagine how something could move through a third. From our point of view, it might look instantaneous, even though it follows rules that we do not understand. These are just ideas at this point, but they are being explored in string theory and other extensions of current physics. Even if we never find a way to truly see faster than light, we might still cheat the system. We might do so in clever ways. One method could involve setting up a vast network of telescopes across space. They would be slowly launched over decades or centuries. Each one of them would observe a different part of the sky. It would send its data back by using normal light speed signals. The trick here is that the telescopes would already be in position. You would not have to wait for the light from a distant galaxy to reach Earth. The telescope would be out there waiting for the light to reach it. This would not give you a real-time observation of everything, but it could greatly expand how much of the universe we can watch as it evolves. Can entanglement transmit images from afar? You can separate entangled particles by kilometers or even across satellites in orbit, and their shared behavior remains perfectly linked. But could we actually use that connection to send or receive information instantly? Could we one day transmit not just a signal but an entire image, a picture from across the universe by using quantum entanglement? If it worked, we would not need giant mirrors or kilometer-long antennas. We could see what is happening on a distant world in real time. It would be 2 points in space connected by quantum rules, passing pure information from one to the other. But the deeper that you go into the science, the more complicated that dream becomes. When 2 particles are entangled, their properties like spin or polarization are undefined. They are undefined until one of them is measured. The instant that you measure one, you also determine the state of the other. This happens no matter how far away it is. But that instant correlation does not transmit anything useful by itself. You cannot control what result you get when you measure the first particle. It is random. The second particle's result will match in a certain way, yes, but there is no way to control it or use it like a message. It is like opening 2 envelopes that always contain matching numbers, but you cannot decide what number to write inside before sealing them. This limitation is why entanglement by itself does not break the speed of light. It does not allow instant communication. if you want to use it for something practical like sending an image from a telescope, you would need a way to control what the particles say to each other. And that is what modern physics says that you cannot do. Still, researchers have not given up. Some scientists are trying to build experiments where entangled particles are used. They are used alongside classical communication channels. In those setups, you might not send the whole image through quantum entanglement, but you could use it to transfer a part of the data, like encryption keys or timing signals with perfect security. That is one of the big ideas behind quantum communication. You send entangled photons between two places, and even if someone tries to intercept the signal, you will know. This is because the entanglement gets disturbed. That is very useful for secure networks on Earth or between satellites, but it is not quite the same as sending a photograph from an alien world. There is also the more exotic idea of quantum teleportation. That name sounds exotic, but it is a real technique. It has been demonstrated many times. Here is how it works. You entangle two particles A and B. Then you bring in a third particle C which holds the information you want to send. You do a special kind of measurement involving A and C. This destroys both of them but transfers the quantum state of C to B. The end result is that particle B, possibly located far away, now behaves exactly like C did. It is as if C has been teleported across space, but again there is a catch. You still need to send classical information alongside the process, and that travels at the speed of light. So even though the quantum part looks instant, the whole thing is still bound by light speed limits. But what if somehow those limits could be overcome? That is where things move from mainstream physics into speculation. Some theories suggest that space and time are just surface-level features of a deeper quantum reality. If that is true, then maybe entanglement is not happening through space. It may be happening outside of it. In that case, maybe distance does not matter at all, and perhaps with the right approach, the barriers that we face now could be sidestepped. Imagine, for instance, a system where two telescopes are entangled at the quantum level, one on Earth and one in deep space. They would be sharing quantum states, maybe pixel by pixel. This would happen without photons actually crossing the vast gulf between them. If such a system could be made to work, it would not be just a new kind of telescope. It would be a whole new way of looking. To be clear, we do not know how to build such a thing. The theories are exciting, but they are not complete. Quantum mechanics is still full of mysteries, and the limits of entanglement are tightly bound by rules we do not yet fully understand. This is especially true when it comes to using it for communication. Some argue that those limits are fundamental, baked into the very structure of physics. Others believe that we are just scratching the surface, and that future technologies might find clever ways around them. Even if entanglement cannot send full images, it might still be useful. It might help telescopes to work better. Imagine an array of space telescopes, each one paired with entangled sensors. They would work together like one giant eye. They could compare signals in ways that classical instruments never could. That kind of system could sharpen images, reduce noise, and allow for much finer detail. This would be useful when studying distant galaxies or exoplanets. We are already seeing hints of this in quantum-enhanced sensing. Some labs are exploring ways to use entangled light to beat the diffraction limit. This is the fundamental barrier to how sharp an image can be. If those techniques scale up, future space telescopes could use quantum tricks. They could use them to see things that today's instruments miss. You would not be sending an image instantly across the galaxy, but you might be making images that are far clearer, more precise, and full of structure. A structure that was invisible before. Would a mirror in another galaxy work? When we look at a galaxy that is 10 billion light-years away, we see its past. We are seeing it as it was 10 billion years ago. But what if the universe could return the favor? What if somewhere far away there was a giant cosmic mirror? And what if by looking into it we could see our own galaxy as it used to be? The laws of physics make something like this possible, at least in theory. If a giant reflective surface existed in a distant part of the universe, a natural or an artificial one, and it reflected light back toward us, then that light would carry an image of what was in front of the mirror long ago. That could include us, or at least our galaxy, and maybe even our solar system. This would depend on the size, the angle, and the position of the mirror. Because of the enormous distances involved, the reflection would act like a time machine. It would show us a younger version of ourselves from billions of years in the past. But where would this mirror be? And what could it be made of? Nothing like it has ever been observed. Natural mirrors do not really exist on this scale, but space is full of objects that reflect or scatter light. Dust clouds, ice particles, and even galaxy clusters can reflect or bend light in complex ways. Some have proposed that dark matter could possibly reflect or echo radiation. This could happen if it interacts weakly with light. Others imagine an alien-built structure, something the size of a planet or larger. It would be placed far out in space to serve as a signal or a beacon. Such a structure might reflect starlight or even produce its own directed light beam. Would we ever be able to see the reflection? The light from our galaxy would have had to travel billions of light years to hit the mirror, and then billions more to return. That means that the reflected image would be even older than most of the galaxies we see. If we could see it, we might be looking at the Milky Way from before the Earth was formed. Not as it was when the dinosaurs walked the Earth. It would be a ghost of our galaxy from a time before our solar system existed. Even if the physics lines up, there are extreme challenges. For one, the mirror would have to be aimed just right. If it were even slightly off, the reflected light would miss us entirely. And it would have to be big, not just large by human standards, but by cosmic ones. A mirror the size of the moon placed a few light years away would not be enough. It would have to be many light years across, more like a galactic scale surface. And it would have to be precisely positioned. The reflected light would be incredibly faint after such a long journey. Picking it out from the background glow of the universe would be like trying to hear a whisper. It would be like trying to hear a whisper in the middle of a hurricane. It would require a telescope that was beyond anything that we have. Still, the idea opens a strange door in our imagination. We cannot send messages faster than light, but we can watch ancient signals arriving. A cosmic mirror, whether it is a cloud, a lensing object, or an alien artifact, could reflect history. It could reflect not just light, but history. It could allow a civilization to see itself as it once was. This could be long after it has changed or disappeared. Some have even wondered whether gravitational lensing could act as a kind of warped mirror. In rare alignments, this can create multiple images of the same object. It is like an echo of light. In theory, light from Earth that passed by a distant galaxy could be bent back. It could be bent back toward us and return millions or billions of years later. These lensing loops are difficult to form and even harder to detect, but they are not impossible. If one of them were discovered, it could let us see our own planet in deep time. It would be like looking into the past through a trick of gravity. Could someone else already be looking at us this way? If an alien civilization built a mirror or a giant lensing array far away and angled it toward the Earth, they might be watching our history unfold in real time. It would be delayed only by the speed of light. They could be seeing an ancient Earth, maybe even the earlier stirrings of life. From their perspective, our present has not happened yet. In fact, if we ever do build extremely powerful telescopes and aim them back, we could aim them back toward areas of space where our own past light might have reached. It is possible that we could spot the reflections of ourselves. In those distant signals, we might not see the Earth or human beings, but we might see the early Milky Way, a galaxy still swirling into form. It would be shaped by collisions and gas clouds and newly born stars. It would be a strange sort of self-portrait painted by the universe itself. It would use light that we did not even know that we had sent. Cosmic repetition. Are we seeing the same galaxies twice? If you were standing in a room full of mirrors, you would see your own reflection. It would be bouncing off the walls over and over, stretching into what seems like infinity. Now imagine that happening not with mirrors but with entire galaxies, not in a room but across the fabric of the universe itself. This is the idea behind cosmic repetition, the possibility that the shape of the universe might cause light to travel in a certain way, so that we see the same galaxies more than once from different angles or at different times. This concept comes from an area of study called cosmic topology. Topology, in basic terms, is the study of how things are connected and shaped. In everyday life, we do not often think about the shape of space. We assume that space goes on and on in all directions, but just because we experience space this way does not mean that it actually behaves like that. This is on the largest scales. The universe could be finite but unbounded like a torus. In such a universe, if you could travel far enough in one direction, you might eventually return to your starting point. But light, which also travels through space, would behave the same way. If space is curved or loops back on itself, a beam of light could travel around the universe. It could travel from a distant galaxy. It could reach us again from another direction, making it seem like a different object. Or more precisely, we might see that same galaxy repeated across the sky, sometimes millions or even billions of years apart in its evolution. Some research teams have scanned the sky looking for signs that certain galaxy patterns repeat. They search for similarities in shape, light, spectra, and age. Anything that might suggest that we are looking at duplicates. If the same piece of the universe shows up more than once in different parts of the sky, it might mean that space is curved or is connected in some way. The universe is not only vast, but it is constantly evolving. A galaxy that we see in one place might look slightly different if we see it again. This is just because time has passed, and the stars within it have moved or died. On top of that, galaxies can look very similar by chance. Many spiral galaxies look almost the same to our telescopes, and distinguishing true repeats from lookalikes is a major challenge. Another complication is cosmic inflation. It's stretched out space so much that even if the universe was curved or wraps around, the distances involved might be far too great for light to have made the full journey yet. That means that the repeating images might exist, but they are still on their way, or maybe they have been stretched beyond our cosmic horizon. But suppose that the universe is small enough and light has had time to wrap around. What would that mean? It would change how we understand the size and shape of everything. Instead of thinking of the universe as an endless stretch of new galaxies, we would have to accept that it is more like a hall of mirrors, a finite space that is giving the illusion of infinity through clever light tricks. It would also mean that our map of the universe is misleading. Some of the millions of galaxies that we see could be echoes, not the originals. We might have much less matter in the cosmos than we think, just that it is seen many times over. That has implications for everything from how we model galaxy formation to how we estimate dark matter and dark energy. If we are counting the same galaxies multiple times, even unknowingly, it could affect the numbers that we base our theories on. This is why cosmic topology, despite sounding abstract, matters deeply to our understanding of space. There is also a philosophical side to all of this. If we live in a repeating universe, it hints at a kind of cosmic symmetry. The universe might not be a random chaos that is spread endlessly outward, but something with a structure and a form, something that, on some deep level, folds back on itself like a grand equation, a place where the end connects to the beginning, where the past might be visible from the future. Mathematicians have come up with many different possible shapes that the universe might take. Some of them are simple, like the torus that was mentioned earlier. Others are far stranger spaces where if you travel in a straight line, you not only loop around, you also flip upside down or appear to be mirrored. These exotic shapes are hard to picture, but can be described with math. Each shape has its own unique signature, and scientists hope that by comparing those models to real data, like the distribution of galaxies or the patterns in the CMB, they might find a match. Interestingly, in 2003, a pair of researchers proposed something. They proposed that the universe might be shaped like a dodecahedron, a 12-sided object like a geometric die. They suggested that the CMB showed hints of this shape, with matching circles on the opposite sides of the sky. Their theory sparked excitement, but further measurements with more precise satellites did not confirm it. Still, it opened the door to other similar ideas, and the search for cosmic repeats continued. If one day we do find that certain galaxies show up in more than one place in the sky, that some light has traveled the full round trip of the cosmos, it would be one of the most profound discoveries in human history. It would mean that we have not only looked into the past, but into a deeper truth about reality, that space is not just a stage for the universe, but an actor in the story too. What we expect to find just beyond the horizon. What do we expect to find just beyond the edge of what we can see? The first guess is the most natural one, more of the same. In fact, the pattern of the cosmos does not suggest that it ends at the visible edge. It is smooth, consistent, and roughly the same in all directions. This kind of smoothness is called isotropy, and it tells us that there is no reason to think that our corner of the universe is special. We do not see a hard edge or a drop-off as we reach the limit. The universe just continues like an ocean that is stretching into a fog. One of the tools that scientists use to support this idea is the cosmological principle. It is the assumption that the laws of physics and the general structure of the universe are the same everywhere. And even though we cannot prove that for places we cannot see, we can test it within our visible range, and so far it holds. That means that if galaxies are arranged a certain way here, they are probably arranged similarly just past the horizon. If the CMB has tiny ripples here, it probably has similar ripples out there too. That lets astronomers build models, mental and digital simulations of what should be waiting. What should be waiting for us in the dark? But the truth is that we are still guessing, and that makes things interesting. Because even though the most likely answer is more of the same, some scientists have asked, what if it is not? What if beyond our light horizon the universe is different in some deep way? Maybe the laws of physics bend a little, maybe the strength of gravity changes, or the charge of the electron. Maybe the fine structure constant is slightly different, a number that controls how atoms behave. It could change chemistry, the way light interacts with matter, and even the color of stars. That would mean that other parts of the universe could look very different, even though they are made of the same building blocks. There are models that suggest that inflation could have created bubbles of space. Other bubbles, which are still expanding beyond our view, might have different settings. On the largest scales, the universe has a web-like pattern. Galaxies and clusters are tied together in filaments with huge voids in between. It looks like a foam or the structure of neurons in a brain. This cosmic web stretches across billions of light years, and yet it is still forming. Galaxies are still merging, clusters are still growing, and gravity is still at work, even in the distant reaches. So what is the pattern just beyond the part that we can see? Simulations of dark matter suggest that the web does not stop. It goes on with the same mix of density and emptiness, structure and randomness. But some models also allow for large, possibly rare structures. Things that we have not seen yet, like supervoids that are bigger than any we have found, or megaclusters that are beyond comparison. There could even be regions where matter is spread more thinly. This would change the local shape of space-time. And if dark energy behaves differently in those regions, it could create strange distortions. Another possibility, which is more speculative but fascinating, is that something ancient lies beyond. Something ancient lies beyond the edge, a kind of fossil from before the CMB. Some theories suggest that if the universe had a phase before inflation, an imprint might exist. An imprint of that era might exist in the form of unusual energy patterns or temperature anomalies. If we ever reach beyond the light horizon, we might stumble into that forgotten era, which is frozen in the silence of space. Every time that we build a better telescope, every time that we gather more light, we add a pixel to our cosmic picture. And by studying the way that light bends, stretches, and shifts, we can sometimes infer things just out of view. In a way, the universe lets us cheat, which gives us clues about what lies beyond. It does so without showing it directly. So the question remains, what do we expect to find just past the horizon? More stars, yes. More galaxies, certainly. But also maybe a different version of everything. Or maybe it is just more of us, an infinite reflection, the signs of a multiverse that are hidden in the deep sky data. In 2000, 7 scientists studying data from the WMAP spacecraft found something odd. They found something odd in the CMB, a large cold spot which was much colder than the areas around it. This cold spot covers a region of space that is hundreds of millions of light years across, and it does not have a clear explanation. Some researchers suggested that it might just be a statistical fluke, a rare patch of space that just happened to turn out that way. But others offered a more dramatic idea. Maybe it is the scar from a collision between our universe and another one. If universes really are born like bubbles in a larger space, then they might sometimes bump into each other as they expand. The result could be a kind of bruise on the fabric of our universe, a region where the temperature, structure, or direction of space has been affected. It would be affected by this contact. When the Planck satellite was launched and began to take even more detailed measurements of the CMB, scientists looked again at the cold spot. The data confirmed that the cold spot is real. It is not an error or a noise, but they still could not agree on what had caused it. Some teams looked for signs of voids, large empty areas of space. These could affect light as it passes through. Others ran simulations to test whether a bubble universe collision could leave exactly that kind of imprint. In addition to the cold spot, there are other patterns in the sky that have raised eyebrows. One of them is the so-called axis of evil, a strange alignment of temperature fluctuations in the microwave background. It seems to point in a particular direction. This is unexpected. The early universe should be more random. Some researchers have suggested that this alignment could also be a trace of an interaction with something that is beyond our universe. Though again, this is very speculative. Another possible clue lies in gravitational waves. If our universe ever did collide with another one, the shock could send ripples. It could send ripples through space-time, the same kind of waves that we now detect from merging black holes. These multiverse waves would be much older and subtler, but some scientists think that they could be found in the future. They could be found in more sensitive gravitational wave detectors. In theory, they might even carry a kind of fingerprint from the other universe. Its size, its shape, or its structure. The multiverse idea shows up naturally in several major theories of physics. The trouble with the multiverse is that it is very hard to test. By definition, most of the other universes would lie beyond our cosmic horizon. But if they leave behind indirect evidence, then maybe we can learn. Maybe, just maybe, we can learn that they are there. Of course, an extraordinary claim requires extraordinary evidence. A cold spot could be caused by a void, an alignment might be a coincidence, and a strange wave could come from some entirely unknown source inside our own universe. And yet some physicists continue to argue that if we keep finding things that do not quite fit our models, and if these same models naturally predict the multiverse, then maybe we are closer to the truth than we think. Even if we never see another universe directly, the possibility changes how we think. It changes how we think about our own. If we are one bubble among many, then perhaps our universe's laws are not the only possible laws. Maybe the constants of nature are just one version out of many. That could help to explain why they seem to be so perfectly tuned for life. In a multiverse, it is not surprising that we find ourselves in one of the few universes where life is possible. The others simply do not have observers who are asking these questions. Are we a part of something that is unimaginably vast, where every possibility plays out somewhere? Or are we alone in a single unique creation? The answer may lie in the sky, not in the places we have already studied, but in the faint forgotten corners, the cold spots, the ripples and the misalignments, the holographic horizon hypothesis. Imagine if the universe in all of its vastness was not what it appeared to be, with its galaxies, its nebulae, and its endless void. Imagine that the deep black sky full of stars was, in a sense, a kind of image, a projection, something that exists because of information stored somewhere else. This is the essence of the holographic horizon hypothesis. It suggests that the reality that we see might be a kind of shadow, the 3 dimensions of space and the 1 of time. It might be cast from a more fundamental lower dimensional surface. To picture this, think of a regular hologram on a credit card. The surface itself is flat, just 2 dimensions, but when you tilt it, you see a 3-dimensional image floating above it. The hologram does not contain the object itself, but it encodes all of the information needed to recreate the image from different angles. The holographic horizon idea works in a similar way, except on a cosmic scale. The surface in this case could be the boundary of our universe, or at least the boundary of the observable part of it. It would store all of the information that describes everything inside. The first seeds of this idea came from black hole physics. In the 1970s, scientists like Jacob Bekenstein and Stephen Hawking were studying black holes. They were studying how black holes store information. They found that the amount of information a black hole can contain is not determined by its volume. Its entropy is not determined by its volume, as you might expect, but it is determined by the area of its event horizon. That is, the surface of a black hole tells you how much information it can hold. This hinted that perhaps information about a 3-dimensional space might be fully stored. It might be fully stored on a 2-dimensional boundary. Later, the physicists Gerard Hooft and Leonard Susskind took this idea and expanded it. They expanded it into the holographic principle. They proposed that not only black holes, but perhaps the entire universe might operate on this rule. The deepest level of physical reality could be described in terms of data that was living on a cosmic boundary. Our universe, with its apparent depth and volume, would be a projection of that underlying information. The horizon in the holographic horizon hypothesis is often compared to the cosmological horizon. If the holographic principle applies here, all of the information about everything we can see might be encoded. It might be encoded on this distant spherical boundary, much like how a planet's surface can hold a map of everything that happens inside. If the hypothesis is correct, then our familiar 3-dimensional world might not be the most fundamental layer. It is full of depth and distance. It could be like the image in a movie, vivid and rich, but ultimately made from something simpler. This does not mean that it is an illusion in the everyday sense. The movie is still real, you can still interact with it, but its structure comes from somewhere else. Testing such an idea is not easy. It is not the kind of thing that you can just build a telescope for. Instead, researchers look for tiny clues in the fabric of reality, clues that might betray its holographic nature. One example is the search for a pixelation in space-time. If space itself is made from information stored on a 2-dimensional surface, there might be a smallest possible unit of space and time of fundamental resolution, and under the right conditions we might detect a slight noise or blurring from this limit. The experiments like the Fermilab holometer were designed to search for such effects. They used extremely sensitive laser interferometers to see if reality jitters at the tiniest scales. So far, no clear sign has been found, but that does not mean the idea is wrong. It might be that the scale at which these effects appear is far beyond our current reach, or that the signs are more subtle than we know how to detect. Another pathway for testing comes from high-energy physics, especially in string theory. String theory naturally incorporates the holographic principle in certain cases, most famously through something called the ADS CFT correspondence, a mathematical duality that was discovered by Juan Maldacena in 1997. This correspondence shows that a certain kind of universe with gravity can be exactly equivalent to a different kind of universe, a universe without gravity that is living in one fewer dimension. If such dualities apply more broadly, it could mean that our own universe has a holographic twin description. It would have this on a cosmic boundary. The implications are enormous. It would mean that the structure of space and time is not fundamental but emergent, like the waves on the surface of water, beautiful, complex, but ultimately built from something deeper. And if time itself emerges from a lower dimensional description, it could change how we think. It could change how we think about beginnings, endings, and the Big Bang itself. If everything that we perceive is the result of information encoded elsewhere, then our role as observers becomes more like decoding a message than directly touching reality. Every galaxy that we see would be a part of a vast, interconnected pattern. It would be projected into our experience from the cosmic edge. In a way, it might solve one of the biggest puzzles in physics: how to reconcile gravity with quantum mechanics. Gravity works best in the smooth, continuous space-time of Einstein's relativity, while quantum theory thrives in discrete probabilistic interactions. If the universe is holographic, then gravity might just be a large-scale effect. It would emerge from more fundamental quantum information processes on the boundary. This would sidestep the direct clash between the two frameworks. Of course, this idea has its critics. Some physicists caution against taking the holographic analogy too literally. They argue that while it is a powerful mathematical tool, it might not describe our real universe. Others point out that until we have clear experimental evidence, it remains a fascinating but unproven speculation. Still, the holographic horizon hypothesis offers a way to bridge deep theoretical gaps. It also sparks the imagination. It invites us to think about the universe not just as an ocean that we swim in, but as a kind of vast and intricate code stored on a surface that we may never directly touch, yet which defines everything that we know. If it is true, then, when we look out into the night sky, we are not just seeing light from ancient stars, we are also glimpsing the unfolding of a grand projection, one that began with the first moments of the universe and continues to this day. It is playing out in a space that might be at its core flatter and stranger than we can yet comprehend. The ultimate deep field if we had unlimited time and tech. We have already gotten a glimpse of this idea with the Hubble Deep Field and the James Webb Deep Field. Those images were captured over several days or weeks. They revealed thousands of galaxies hiding in what once looked like nothing at all. Each tiny point of light turned out to be an entire galaxy full of stars, planets, and unknown histories. It shocked even the scientists who had planned the observations. But those images are limited by time and by technology. If we had none of those limits, we could push deeper still. The first thing that we would notice is how the picture slowly becomes richer and more complex. The longer that we stare, the fainter a light that we collect. The oldest galaxies would slowly appear one by one, like faint stars emerging at dusk. Eventually, the entire field would glow with countless galaxies. each one a city of stars in a universe that no longer looks empty. But it would not stop there. Our perfect telescope would not only collect visible light, it would see in all wavelengths. That means that we could look at things that are completely invisible to human eyes. The cold gas clouds glowing in the radio band, the supernova remnants flickering in X-rays, and the baby galaxies still forming inside thick cocoons of dust. They would be visible only in the infrared. The field would become a multi-layered portrait. Every slice of the spectrum would add new information, not just about where things are, but how they behave, what they are made of, and how they have changed over time. And then we would see motion. With perfect tools and unlimited time, we would not just take a still image, we would watch the sky like a time-lapse. Black holes would light up as they consume nearby gas. The sky would no longer be static. It would pulse, shift, and grow like a living thing. Eventually, as our view deepened, we would begin to see the very first stars. These population 3 stars have never been seen directly, but in our perfect deep field they would shine. We would see them blink into existence, burn with a fierce intensity, and then collapse into black holes or explode as giant supernovae. These early stars would light up the cosmic dark ages. They would reveal a universe that is still mostly empty but beginning to take shape. Beyond even those first stars lies the edge of visibility. With our ultimate tools, we could see the CMB not just as a uniform glow, but as a detailed landscape, a map of temperature, ripples, density variations, and quantum seeds. These would grow into the structure that we observe today. And maybe, if our instruments are good enough, we could go even deeper. We could go past the microwave background to see traces of what came before. Maybe even signals from before the Big Bang, if such a thing is possible. With perfect tools, we could also look forward. We could observe not just what the galaxies were, but what they are becoming. Over the ages, we would see star formation slow down. We would watch galaxies fade, merge, and drift apart as the universe expands. Eventually, we might even see the large-scale structure of the universe begin to empty out. This would happen as galaxies move beyond our cosmic horizon. They would leave behind a quieter, lonelier sky. And if we go far enough into the future, the light itself will change. The stars will run out of fuel. The black holes will grow swallow and eventually evaporate. In the very distant future, only the cold remnants will remain. The white dwarfs cooling into black lumps, the dead planets drifting alone, and perhaps a few exotic particles flickering in the void. Our deep field, which once burst with light and energy, would slowly dim. It would become a record of everything that was. A time capsule of a living cosmos that was gradually falling asleep. Even in the dark, though, there might be surprises. Some theories suggest that new universes could bubble into existence far away from us, in a deep enough field with tools that can detect even the smallest changes in space-time. We might see the beginnings of such events, the tiny distortions, the strange flashes, or the unexplained patterns. Our ultimate telescope might become the first device to spot another universe being born. The future missions like the Roman Space Telescope and the ground-based observatories like the Extremely Large Telescope will go much further. They will go much further than the Hubble and the Co. But we are still very far from the ultimate deep field, a window not just into space but into time, physics, and the unknown, the technology of the future's future. If we imagine the far future, not just 100 or 1,000 years from now, but tens of thousands, maybe millions, we enter a world where the tools of science do not just improve, they evolve into something that is beyond anything that we have ever built. A telescope of the future's future would not be just a bigger version of what we already have. It would be something entirely different. A tool that does not just look deeper, but changes how we even define seeing. One of the ideas is building telescopes the size of moons, or even larger. A telescope that is that size would be so powerful, It could spot Earth-like planets around stars on the far side of the galaxy. Of course, building something that massive would not be easy. Even getting the parts into space today is a struggle. But in the far future, with technologies we do not yet have, like self-replicating machines, space-based construction, or materials grown from atomic layers, it becomes more likely. An advanced civilization might not build one giant telescope all at once, but let it grow piece by piece. A swarm of satellites could fly in formation, acting as one single lens. Lasers could keep them perfectly aligned, spreading across thousands of kilometers. They would collect light together like one vast eye pointed at the stars. Some scientists have already begun imagining this, calling them aperture arrays. They do not need to be solid mirrors. They just need to act together, synchronized to the smallest fraction of a second. These floating telescopes could stretch across the orbit of a planet, or even form rings around stars. Their view of the universe would be sharp enough to watch a volcano erupting on an alien world, or to read the rings of atoms around distant black holes. But even these are small compared to what might come next. The real leap is when the telescopes are not just large, they become cosmic. A telescope the size of a planet is already huge. A telescope the size of a star is bigger still. But what about one the size of a galaxy? That sounds impossible, but it is an idea that is worth exploring. A civilization that is advanced enough to control the stars or to harvest energy from entire solar systems. Something that we might call a Type 3 on the Kardashev scale. It would not be limited by earthbound thinking. They could use the gravity of stars or the orbits of entire solar systems to arrange giant lenses. They could arrange mirrors or detectors across light years of space. They might use gravitational lensing to their advantage, but at a completely different scale. Instead of building a telescope to take advantage of the sun's lensing, future civilizations could do the same with many stars, maybe even black holes. If it was carefully mapped and coordinated, an entire network of these lenses could provide a view of the universe that is nearly perfect down to its smallest details. The telescopes would no longer be just tools to gather light. They could become instruments that track time scan, quantum fields, or measure the fabric of space. They could do so with such precision that even the faintest ripples of ancient events could be recorded. The echoes of a galaxy forming the flicker of a long-dead civilization. The telescope of a Type 3 civilization could be a giant sensor web. It would be spread across an entire star cluster. It would be sensitive to all kinds of signals: light, neutrinos, gravitational waves, magnetic fluctuations, and even forms of energy that we do not know about yet. Imagine a civilization spreading through the galaxy, not to colonize, but to observe. Every star system becomes a part of a larger instrument. Each planet houses a part of a detector. Every moon carries mirrors, cameras, or sensors. They might not need to send spaceships anymore. Instead, they see everything from where they are. The whole sky becomes a canvas of living data. And what would they be looking for? Maybe the birth of a new universe, the first flicker of life on a newly formed world, or the last collapse of a dying galaxy. They might use their instruments to test the limits of physics itself, zooming in on the edges of black holes, watching the quantum fluctuations that are rippling across space, or trying to find signs of a structure beyond the observable universe. They might not use eyes at all. Their senses could extend into dimensions that we cannot perceive, like trying to explain color to someone who sees only in black and white. It is even possible that these civilizations already exist, and that we are inside one of their telescopes without even knowing it. If a network of observation tools is large enough and subtle enough, we could pass right through it like insects flying through a vast machine. Perhaps the universe is already being watched by instruments that are so powerful and advanced that they do not disturb anything at all. They only observe. To us, space seems empty, but to them, every atom, every particle, and every ray of light is data. We build telescopes one at a time, metal glass mirrors and sensors. Each one opens a new window, but the sky remains mostly dark, mostly unknown. Still, we can imagine. We can look ahead, not just years or centuries, but into the deep future. A time when seeing the universe means becoming a part of it. When our tools are no longer bound by size, weight, or cost. When observation becomes an act of presence, not just a science. When telescopes stretch across the stars and the entire cosmos becomes the lens through which we search for meaning. What would the back of the Big Bang look like? We are always looking outward. Every telescope on Earth or in orbit points toward the sky. It searches for signals that have traveled across time and space to reach us. The farther that we look, the further back in time that we go. And when we look deep enough past all of the stars and galaxies, we find the CMB. But what is behind that wall? In everyday life, we are used to being able to turn things around, to flip them over, and to look behind and underneath. But in cosmology, the word behind stops making sense. The Big Bang was not an explosion that happened in space. It was the beginning of space and time itself. There is no outside, there is no direction to point a telescope and say, let's look behind it. Still, scientists have tried to imagine what the early moments might have looked like. By using mathematics, we can roll the universe back in time, shrinking galaxies, heating up particles, and pushing everything closer together. Eventually, we reach a point where the laws of physics begin to break down. A state of energy and density that is so extreme that our current theories cannot describe it. This is the limit of our vision. But there is also a more radical way to think about this question. Some physicists have asked whether the Big Bang is even the beginning. Maybe it is not a wall, but a bridge. There are theories that suggest that the universe did not start from nothing, but from something else, another state, or another phase. In these models, the Big Bang is just a transition point, like ice turning into water. Before the bang, there may have been a contracting universe, a cosmic bounce or a timeless quantum field that was fluctuating until something burst into existence. If that is true, then behind the Big Bang becomes a meaningful phrase, not in the literal sense of turning around and seeing what is there, but in the sense of tracing the cosmic timeline further back. The Big Bang might be the aftershock of something else. Some ideas come from string theory and quantum gravity. In these frameworks, the Big Bang is not a point of infinite density, but a kind of phase change in the geometry of space. Think of steam turning to water. If the early universe underwent such a transition, then it might be possible to model what came before. One idea is the ekpyrotic model. In this theory, our universe was born from the collision of two higher dimensional membranes. They collided in a wider space. The impact created the energy and matter that we now observe. In this view, the Big Bang is just the visible side of a much larger story, the aftermath of a cosmic event that took place in dimensions that we cannot access. Others suggest that time itself may have behaved differently in those early moments. Instead of flowing from a past to a future in a single direction, time may have been more like a landscape, a place where different directions were possible but collapsed into one as the universe cooled. In this picture, looking behind the Big Bang is like trying to look at the backside of time itself. These ideas are hard to picture and even harder to test. Even if there is no light from before the CMB, the universe may still hold clues, in the way that galaxies cluster or in the faint signals of quantum fields. There may be whispers of what existed before. What if the universe ends just out of sight? Space feels like it has no boundary, no edge, and no end. But that sense of infinity is only based on what we can see, and what we can see is limited. What if there is nothing beyond? What if just past the cosmic horizon space does not continue forever? What if the universe ends not in the distant future, but right now, just out of sight. For a long time, scientists have asked whether the universe is infinite or finite. There are several ways that the universe could be finite and still seem infinite to us. One idea is that space curves back on itself, but what if space does not loop back? Maybe it just stops, not with a wall or a drop-off, but with a region where there simply is no more space. Just like how a painting has a frame or a video has an edge, maybe the universe only exists out to a certain scale and then it does not. If this is true, it would completely change how we think about everything. For one thing, it would mean that the universe is much smaller than we thought. Maybe instead of being one small dot in a vast, endless ocean of galaxies, we are actually near the edge. Or maybe we are right in the middle of the whole thing. But there is still only a limited number of galaxies, a limited number of stars, and a limited amount of time and space. It would also mean that some of the biggest assumptions in physics might need to be rethought. A lot of our theories, especially in cosmology, depend on the idea that the universe is the same everywhere. But if the universe ends somewhere out there, then that symmetry breaks. There is a place where space stops. That would make our location special in some way, not because we are important, but because we are somewhere inside a finite object, not just floating in an endless void. Another thing that this raises is the question of why the universe would end at all. What would make it stop? Is there some kind of boundary condition that sets the outer limits? Is there a deeper reality that is outside of it? A place where other universes exist, or where ours was created from? These questions quickly move from physics to philosophy. They touch on the nature of existence itself. Of course, one of the reasons that we tend to imagine the universe as infinite is because it is easier. It is easier to think that way. It avoids the uncomfortable ideas about edges, endings, and limits. An infinity lets things continue forever. It means that there is always more to explore, more to learn, and more to see. A finite universe, especially one that ends just out of reach, feels a bit like a trick, like a stage that looks vast from the front row, but turns out to be shallow when viewed from behind. What would happen if we ever got close to the edge? We could not travel there. That is impossible with current technology. But what if we could observe it somehow? What would it look like? Would it just be a darkness? Would space become thinner or behave differently? Would the laws of physics break down? No one knows, and maybe we will never know. But the fact that the edge could be there just outside our view adds a kind of mystery. It adds a mystery to everything that we observe. It also challenges our place in the universe. If we are inside a finite cosmos, then it might mean that the universe itself had to be created. It had to be created in a specific way. Maybe it came from something else. Maybe it is a part of a larger system. Or maybe it just is, and we will never understand why. That kind of uncertainty is not easy to accept, but it is a part of science. What we think of as the universe is still just a picture that we build from what we can see. That picture is rich and detailed, but it is also incomplete. There could be strange truths just beyond the edge of that frame, and if that is the case, then all of our telescopes, all of our maps, and all of our theories are happening inside something that is at its heart limited. The idea that the universe might end just beyond what we can see does not make it smaller. It does not make it smaller in a practical sense. It is still more than we can ever visit or explore. But it adds a weight to the question of how we fit into the whole thing. It makes the mystery more immediate. It makes the silence of deep space feel a little more personal, because maybe there is a line. Maybe, just maybe, there is a line out there where everything stops, and we are on the inside trying to make sense of it all. What sort of exciting future discovery on this topic are you looking forward to?